Picture this, a galaxy shimmering in the dark void of space. At its heart, a bar of light stretches across its center like a cosmic backbone, glowing with the energy of countless stars and mysterious forces at work. Have you ever wondered why these galactic bars exist? How did they form, and what role do they play in shaping the universe? This isn't just about stars or gas clouds, it's about the mechanisms of the cosmos, the very physics that govern the birth and evolution of galaxies. And here's the kicker, these bars might just be the key to understanding some of the universe's deepest mysteries. So buckle up, because what you're about to learn will change the way you see the universe forever. Let's start with the basics. When we think about galaxies, most of us picture a classic spiral galaxy, those beautiful swirls of stars and gas that look like pinwheels scattered across the sky. But if you take a closer look at many of these galaxies, something interesting stands out. Right in the middle, there's often a straight, elongated structure cutting through the core, almost like a glowing bar. This structure isn't just a random feature. It's what astronomers call a galactic bar, and it's far more important than it might seem at first glance. To understand galactic bars, you first need to grasp how galaxies form and evolve. Galaxies are born from massive clouds of gas and dark matter. Over billions of years, these clouds collapse under their own gravity, spinning and flattening into disk-like shapes. But here's the twist, not all galaxies end up as perfect spirals. Many develop these central bar structures, and scientists have spent decades trying to figure out why. The answer lies in a combination of gravitational dynamics, the movement of stars, and even the influence of mysterious dark matter. Galactic bars form when the orbits of stars in a galaxy's disk begin to align in a specific way. Instead of moving in random directions, the stars start to follow elongated paths that create the appearance of a bar. This alignment doesn't happen by accident. It's the result of complex gravitational interactions within the galaxy, and it can take billions of years to fully form. But here's where it gets even more fascinating. These bars aren't just decorative. They play a critical role in the life cycle of a galaxy. Think of a galactic bar as a kind of conveyor belt, funneling gas and dust toward the galaxy's center. This process can trigger massive bursts of star formation, lighting up the core of the galaxy with new stars. Over time, this activity can reshape the entire structure of the galaxy, influencing everything from its spiral arms to its overall brightness. You might be wondering, why do some galaxies have bars while others don't? That's a great question, and it's something astronomers are still trying to fully understand. What we do know is that bars are more common in galaxies with a lot of mass and older stars. They're also influenced by the galaxy's environment. For example, interactions with nearby galaxies can disrupt the gravitational balance and help kickstart the formation of a bar. Dark matter, that mysterious substance that makes up most of the universe's mass, also plays a role. While we can't see dark matter directly, we know it surrounds galaxies in massive halos, and its gravitational pull can help stabilize or destabilize the formation of a bar. It's a cosmic dance between visible and invisible forces, and the result is one of the most striking features in the universe. What's even more mind-blowing is how galactic bars evolve over time. In the early stages, a bar might be short and faint, barely noticeable against the galaxy's background. But as time goes on, it grows longer and brighter, drawing in more gas and stars. Eventually, the bar can become so dominant that it reshapes the entire galaxy, transforming a classic spiral into something entirely new. Scientists have even discovered that bars can fade away after billions of years, leaving behind a galaxy that looks completely different from its original form. But why does any of this matter? Why should we care about these bars of light in distant galaxies? The answer lies in their role as cosmic laboratories. By studying galactic bars, scientists can learn more about the fundamental forces that shape the universe. These structures offer clues about how galaxies grow, how stars are born, and even how dark matter interacts with visible matter. They're like a window into the past, showing us what the universe looked like billions of years ago and helping us predict its future. Galactic bars also have a direct impact on the supermassive black holes that lie at the centers of most galaxies. As the bar funnels gas toward the core, it can feed the black hole, triggering powerful outbursts of energy. These outbursts can influence the surrounding galaxy, pushing gas and dust outward and potentially slowing down star formation. It's a feedback loop that connects the smallest scales of the universe, black holes, with the largest, entire galaxies. And here's something to think about: not all bars are created equal. Some are smooth and symmetrical, stretching gracefully across the galaxy's core. Others are twisted or broken, their shapes distorted by gravitational forces. Each one tells a different story about the galaxy's history and the events that have shaped it. For example, a distorted bar might indicate a past collision with another galaxy, while a smooth bar could suggest a more stable, isolated evolution. But there's still so much we don't know. Why do some bars last for billions of years while others fade away? What triggers the initial alignment of stars that creates a bar? And how do these structures interact with the larger cosmic web that connects galaxies across the universe? These are the questions that keep astronomers awake at night, and every new discovery brings us one step closer to understanding the mysteries of the cosmos. And yet, despite all the research, galactic bars remain one of the most mysterious and intriguing features of the universe. They're a reminder that even in the vastness of space, there are still secrets waiting to be uncovered, still questions that challenge our understanding of the cosmos. So the next time you look up at the night sky, remember, those distant galaxies aren't just beautiful, they're full of mysteries that could hold the key to the universe itself. As we dive deeper into the mystery of galactic bars, it's crucial to explore how these structures interact with their surrounding environment. One of the most captivating aspects of galactic bars is their ability to act as dynamic engines within their host galaxies, driving processes that extend far beyond their immediate vicinity. To understand this, we need to examine how these bars influence the gas, stars, and dark matter in their surroundings. Galactic bars play a pivotal role in redistributing material within galaxies. Through their gravitational pull, they act like cosmic highways, channeling gas from the outer regions of the galaxy toward the central core. This inflow of gas isn't just a subtle nudge, it's a transformative process that fuels star formation on a massive scale. As the gas gets compressed and heated during its journey inward, it triggers the collapse of molecular clouds, birthing new stars in the galaxy's heart. This process, known as starburst activity, can light up the central region of a galaxy, making it shine more brightly than ever before. Interestingly, this funneling effect doesn't just stop at star formation. The inflow of gas also feeds the supermassive black hole that lies at the core of most galaxies. When this black hole consumes the gas, it releases tremendous amounts of energy in the form of radiation and outflows. These energetic events are known as active galactic nuclei, AGN, and can dramatically alter the galaxy's evolution. The energy released by the AGN can blow away nearby gas and dust, effectively quenching star formation and leaving behind a galaxy that is more passive and less active. This feedback mechanism creates a delicate balance, as the bar both fuels and regulates the life cycle of its galaxy. But the influence of galactic bars doesn't stop at the core. They also shape the outer regions of galaxies, particularly the spiral arms. The gravitational forces exerted by the bar create resonances that ripple outward, organizing the movement of stars and gas into the beautiful, symmetric spirals we see in galaxies like the Milky Way. These spirals aren't static structures. They're constantly in motion, with stars and gas flowing along their arms in a dance choreographed by the galaxy's bar. Without this organizing influence, many galaxies might lose their iconic spiral shapes, becoming chaotic and disorganized. Let's not forget about dark matter, the invisible substance that makes up the bulk of a galaxy's mass. Although we can't see or touch dark matter, we know it exerts a powerful gravitational force, shaping the behavior of galaxies on a cosmic scale. Galactic bars interact with the dark matter halo surrounding a galaxy, creating subtle shifts in the distribution of this mysterious material. Some theories even suggest that dark matter helps stabilize galactic bars, keeping them intact over billions of years. Without dark matter, these bars might collapse or fade away, drastically altering the galaxy's structure. One of the most intriguing questions about galactic bars is their role in the long-term evolution of galaxies. As these bars grow and change over time, they can transform a galaxy's entire identity. For instance, a galaxy that starts as a classic spiral might develop a prominent bar, funneling gas toward its core and triggering a burst of star formation. Over billions of years, this process can use up most of the galaxy's gas, leaving behind an older, more passive galaxy with fewer new stars. Some astronomers believe that this is how many lenticular galaxies, a type of galaxy that sits between spirals and ellipticals, are formed. The life cycle of a galactic bar is also a fascinating topic. Bars aren't permanent features. They evolve and, in some cases, disappear entirely. This happens because the gravitational forces that create the bar can also work to destabilize it over time. For example, as the bar funnels gas toward the galaxy's core, it can deplete the material needed to maintain its structure. Additionally, interactions with other galaxies, such as mergers or close encounters, can disrupt the bar, breaking it apart or transforming it into something new. This dynamic nature makes galactic bars one of the most active and influential features in the universe. When we look at the Milky Way, we see that it, too, has a central bar. Our galaxy's bar spans tens of thousands of light-years, cutting through its center like a glowing bridge of stars and gas. Studying the Milky Way's bar gives astronomers a unique opportunity to understand these structures up close. For example, observations of the Milky Way's bar have revealed that it rotates at a speed of about 100 kilometers per second, taking hundreds of millions of years to complete a single rotation. This rotation drives the movement of stars and gas throughout the galaxy, influencing everything from the shape of its spiral arms to the rate of star formation in its core. But there's more. The study of galactic bars isn't just about understanding individual galaxies. It's about uncovering the larger patterns that govern the universe. By comparing bars in different galaxies, astronomers can identify trends and correlations that reveal how galaxies form and evolve on a cosmic scale. For instance, we've learned that bars are more common in older, more massive galaxies, suggesting that they play a key role in the later stages of galactic evolution. We've also discovered that bars are less common in dense galaxy clusters, where interactions with neighboring galaxies can disrupt their formation. As we continue to study galactic bars, new technologies and telescopes are opening up exciting possibilities. Instruments like the James Webb Space Telescope are allowing us to see deeper into space than ever before, capturing detailed images of galaxies with bars in various stages of development. These observations are helping scientists piece together the story of how bars form, evolve, and interact with their surroundings, shedding light on one of the most captivating mysteries of the cosmos. And yet, despite all we've learned, galactic bars remain a source of wonder and intrigue. They're a testament to the complexity and beauty of the universe, a reminder that even in the vastness of space, there are structures and patterns that connect everything together. From the stars that shine in their cores to the dark matter halos that surround them, galactic bars are a window into the forces that shape the universe, and they remind us that there's still so much more to discover. The enigma of galactic bars continues to challenge and expand our understanding of the cosmos. These structures, as mesmerizing as they are complex, encapsulate the dynamic processes that drive the evolution of galaxies. To grasp the full scope of their significance, we must delve further into their physical properties, formation mechanisms, and broader implications for galactic dynamics. One fascinating aspect of galactic bars is their ability to generate resonances within a galaxy. Resonances are regions where the gravitational influence of the bar aligns with the orbital motions of stars and gas. These resonances can have profound effects, shaping the distribution and movement of matter within the galaxy. A key example is the corotation resonance, where the bar rotates at the same angular speed as the surrounding material. This region acts as a boundary, separating the inner regions of the galaxy from the outer disk. Within this boundary, stars and gas are more directly influenced by the bar's gravitational pull, creating unique patterns of motion and density. Other types of resonances, such as the inner Lindblad resonance, ILR, and the outer Lindblad resonance, OLR, play equally significant roles. The ILR occurs closer to the galactic center and often coincides with regions of intense star formation. Here, the compression of gas clouds by the bar's gravitational forces leads to the creation of dense, star-forming regions. In contrast, the OLR lies farther out in the galactic disk and can act as a barrier, preventing material from flowing inward. Together, these resonances create a complex interplay of forces that define the structure and behavior of the galaxy. Understanding these resonances is crucial for deciphering the life cycle of galactic bars. Observations have shown that bars can grow or shrink over time, depending on how they interact with the surrounding material. For example, as the bar transfers angular momentum to the outer disk, it can become more elongated and prominent. This process, known as secular evolution, is a slow but transformative force that reshapes the galaxy over billions of years. Interestingly, the size and strength of a bar are also influenced by the properties of the galaxy's disk. Galaxies with more massive and colder disks, where stars and gas move in relatively stable, circular orbits, are more likely to develop prominent bars. In contrast, galaxies with hotter, more chaotic disks may struggle to sustain a bar, as the random motions of stars and gas counteract the organizing influence of the bar's gravitational pull. This delicate balance highlights the interconnectedness of galactic structures, where each component influences the others in a cosmic feedback loop. As we observe galaxies across the universe, we find that bars are incredibly diverse in their appearance and behavior. Some galaxies feature long, straight bars that dominate their central regions, while others have shorter, more curved bars that blend seamlessly into their spiral arms. This diversity reflects the myriad factors that shape a galaxy, from its initial conditions during formation to its interactions with other galaxies over time. Galaxy interactions, in particular, can have a profound impact on the formation and evolution of bars. When two galaxies pass close to each other or merge, their gravitational forces can distort their shapes, triggering the development of a bar. These interactions can also enhance the inflow of gas toward the galactic center, fueling bursts of star formation and the growth of the central black hole. In some cases, these events can even lead to the formation of double bars, where a smaller, secondary bar resides within the larger primary bar. Double bars are rare but offer valuable insights into the complex dynamics of galactic evolution. One of the most compelling questions about galactic bars is their role in the overall evolution of the universe. As we peer deeper into space and further back in time, we see that bars were less common in the early universe. This suggests that they are a relatively recent phenomenon, emerging as galaxies matured and their disks became more stable. The increasing prevalence of bars over cosmic time provides clues about the processes that govern galaxy formation and evolution. For example, the appearance of bars may be linked to the depletion of gas in the universe. In the early universe, galaxies were rich in gas, which fueled rapid star formation and chaotic interactions. As this gas was gradually consumed or expelled, galaxies became more stable, allowing bars to form and take on a more prominent role. This transition marks a shift from a universe dominated by intense, chaotic activity to one characterized by more structured and organized systems. Another intriguing aspect of galactic bars is their potential role in the formation of supermassive black holes. By channeling gas toward the galactic center, bars can provide the raw material needed for black holes to grow. Over time, these black holes can become some of the most massive objects in the universe, exerting a profound influence on their host galaxies. The feedback from black hole activity, whether in the form of powerful jets or intense radiation, can shape the surrounding environment, regulating star formation and altering the galaxy's appearance. Moreover, galactic bars are closely tied to the concept of galactic secular evolution, which emphasizes the gradual, internal processes that drive change within galaxies. Unlike dramatic events like mergers or collisions, secular evolution operates on much longer timescales, allowing us to study the slow but steady transformation of galaxies. Bars are a central feature of this process, acting as agents of change that redistribute material and energy within the galaxy. Despite all we've learned about galactic bars, many mysteries remain. For instance, we still don't fully understand why some galaxies develop bars while others do not. Is it purely a matter of initial conditions, or do external factors like environment and interactions play a more significant role? Additionally, the exact mechanisms that govern the growth and dissolution of bars are still the subject of intense study. Observations and simulations suggest that bars can persist for billions of years, but they can also dissolve relatively quickly under certain conditions. Unraveling these mysteries will require more advanced observations and theoretical models. In the coming years, new technologies and missions promise to revolutionize our understanding of galactic bars. Instruments like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will provide unprecedented views of galaxies, allowing us to study their bars in greater detail than ever before. These observations will help answer some of the most pressing questions about how bars form, evolve, and interact with their surroundings, bringing us closer to a complete picture of their role in the cosmos. As we continue to explore the universe, galactic bars stand as a reminder of the complexity and beauty of the cosmos. They are not just structures of stars and gas, they are dynamic, evolving systems that reveal the intricate dance of forces shaping our universe. The study of galactic bars is far from over, and each new discovery adds another layer to the rich tapestry of our understanding. The mystery of galactic bars is a story that intertwines the past, present, and future of galaxies, revealing their intricate dynamics and pivotal roles in shaping the cosmos. Their significance is multifaceted, influencing everything from the flow of matter within galaxies to the evolution of their overall structure. As we delve deeper into their properties and implications, we uncover new layers of complexity that challenge our understanding of the universe. One area that continues to intrigue researchers is the connection between galactic bars and dark matter. Dark matter, an invisible substance that makes up a significant portion of the universe's mass, plays a crucial role in shaping the gravitational environment of galaxies. While it does not interact with light or ordinary matter in conventional ways, its gravitational effects are profound, influencing the formation and stability of bars. The presence of a dark matter halo surrounding a galaxy can affect the dynamics of its bar. Some studies suggest that dark matter halos can help stabilize bars, allowing them to persist over billions of years. However, other research indicates that interactions between the bar and the dark matter halo can lead to the gradual dissolution of the bar. This interplay between visible and invisible matter highlights the complexity of galactic dynamics and underscores the importance of understanding dark matter's role in shaping the universe. Furthermore, the relationship between bars and the spiral arms of galaxies is another fascinating topic of study. Spiral arms, the iconic structures that give many galaxies their stunning appearance, are often linked to the presence of a bar. In barred spiral galaxies, the bar can act as a driving force for the spiral arms, channeling material outward and creating density waves that propagate through the disk. These waves compress gas and dust, triggering bursts of star formation and giving rise to the bright, star-filled regions we associate with spiral arms. The interplay between bars and spiral arms is not just a matter of aesthetics. It has profound implications for the life cycle of galaxies. By funneling material into the spiral arms, bars contribute to the ongoing process of star formation, ensuring that galaxies remain active and vibrant over time. At the same time, the movement of material within the galaxy can redistribute angular momentum, altering the overall structure and dynamics of the system. Interestingly, not all galaxies with bars have prominent spiral arms. Some barred galaxies, known as barred lenticular galaxies, lack the distinct spiral structures found in their more visually striking counterparts. These galaxies provide a unique window into the diversity of barred systems, offering clues about how different galactic environments and evolutionary histories shape their appearance and behavior. Another critical aspect of galactic bars is their influence on the chemical composition of galaxies. As bars funnel gas toward the center, they bring together material from different regions of the galaxy. This mixing process can lead to a more uniform distribution of chemical elements, enriching the central regions with heavy elements produced by previous generations of stars. Over time, this chemical evolution can have a profound impact on the types of stars that form and the overall properties of the galaxy. The study of galactic bars also intersects with the broader field of galaxy classification. Astronomers use the Hubble sequence, a classification system developed by Edwin Hubble, to categorize galaxies based on their appearance. Bars play a prominent role in this system, with barred spirals designated as SB galaxies. Within this category, further distinctions are made based on the tightness of the spiral arms and the prominence of the bar, reflecting the diverse range of barred galaxy types. The formation of bars is not limited to massive galaxies. Observations have revealed that smaller galaxies, known as dwarf galaxies, can also host bars. While these bars are typically less prominent and shorter-lived than those in larger galaxies, they provide valuable insights into the universality of bar formation processes. Studying bars in dwarf galaxies can help researchers understand how factors like galaxy size, mass, and composition influence the development and evolution of these structures. In addition to their scientific importance, galactic bars are a source of aesthetic and philosophical wonder. They remind us of the incredible variety and complexity of the universe, where even the smallest details can have far-reaching consequences. The sight of a barred galaxy, with its intricate interplay of light and structure, inspires a sense of awe and curiosity that drives our exploration of the cosmos. As we look to the future, the study of galactic bars promises to remain a vibrant and evolving field. Advances in technology, from ground-based observatories to space-based telescopes, will enable us to observe galaxies in unprecedented detail. These observations, combined with sophisticated simulations and theoretical models, will shed light on the many unanswered questions about bars, from their formation mechanisms to their role in the broader context of cosmic evolution. The story of galactic bars is far from complete. Each discovery adds another piece to the puzzle, deepening our understanding and opening new avenues of inquiry. These structures, seemingly simple at first glance, are gateways to the profound mysteries of the universe, revealing the intricate connections that bind galaxies together and shape their destinies. In the grand tapestry of the cosmos, galactic bars are threads that weave together the past and future, order and chaos, light and shadow. They are reminders of the complexity and beauty of the universe, challenging us to look closer, think deeper, and never stop exploring. With each new observation and insight, we come closer to unraveling their mysteries, illuminating the hidden forces that govern the dance of galaxies across the vast expanse of space. The study of galactic bars not only deepens our understanding of how galaxies evolve but also provides a unique perspective on the interconnected nature of cosmic phenomena. To truly appreciate the importance of these structures, we must consider the ways in which they influence, and are influenced by the universe at large. Galactic bars are not isolated phenomena. They exist as part of a vast cosmic ecosystem, interacting with neighboring galaxies, dark matter, and even the large-scale structure of the universe. One of the most intriguing aspects of galactic bars is their role in galactic interactions and mergers. When galaxies interact, whether through close encounters, tidal forces, or outright mergers, their internal dynamics can be dramatically altered. Bars often emerge or are enhanced during these interactions as gravitational forces distort the galaxy's disks. This process is particularly evident in galaxy pairs and groups, where the mutual gravitational pull can induce the formation of bars in both interacting members. In some cases, interactions can even trigger the formation of double bars, a phenomenon where a smaller, secondary bar forms within the primary bar. These nested bars are fascinating because they introduce an additional layer of complexity to a galaxy's dynamics. The secondary bar, which typically rotates at a different speed than the primary bar, can create unique patterns of gas flow and star formation. This phenomenon raises questions about how these dual structures influence the central regions of galaxies, and whether they play a role in the development of supermassive black holes. Supermassive black holes, which reside at the centers of most galaxies, have a deeply interconnected relationship with galactic bars. As bars drive material toward the galactic nucleus, they can feed the black hole, triggering periods of intense activity known as active galactic nuclei, AGN. These bursts of energy release enormous amounts of radiation, often outshining the entire galaxy. Over time, this process can regulate star formation by heating and expelling gas, a phenomenon known as feedback. The interplay between bars and black holes is a prime example of the feedback loops that are so common in cosmic systems. Bars influence black holes by funneling material, while the energy released by the black holes can, in turn, affect the bar's structure and longevity. Understanding these feedback loops is crucial for building a comprehensive picture of galactic evolution, as they help explain why galaxies appear the way they do. Another fascinating aspect of galactic bars is their potential to influence galaxy clusters, the massive conglomerations of galaxies that dominate the large-scale structure of the universe. Within clusters, interactions between galaxies are common, and bars may play a role in shaping the dynamics of these environments. For instance, bars could facilitate the transfer of material between galaxies, influencing the overall distribution of gas and stars within the cluster. This possibility has only recently begun to be explored, but it underscores the far-reaching impact that bars can have beyond their host galaxies. The role of galactic bars extends to the very formation of galaxies themselves. In the early universe, when galaxies were still forming from the primordial gas left over from the Big Bang, bars may have acted as catalysts for structure formation. By organizing the chaotic motions of gas and stars, bars could have helped shape the first galaxies, laying the groundwork for the complex systems we observe today. Studying bars in high-redshift galaxies, those that are far away and thus seen as they existed billions of years ago, provides a window into these formative stages of galactic evolution. High-redshift observations have revealed that bars were less common in the early universe than they are today. This trend suggests that bars develop over time, perhaps as galaxies grow more massive and settle into stable disks. However, the exact mechanisms behind this evolution remain a topic of active research. Some theories propose that bars emerge as galaxies reach a critical threshold of rotational velocity and mass, while others emphasize the role of environmental factors, such as interactions with neighboring galaxies. One of the most exciting developments in the study of galactic bars is the use of advanced computer simulations to model their formation and evolution. These simulations allow researchers to explore how different factors, such as the distribution of dark matter, the amount of gas, and the presence of other galaxies, affect bar dynamics. By comparing the results of simulations with observations, scientists can test their theories and refine their understanding of the processes at work. For example, simulations have shown that the strength and longevity of a bar can depend on the ratio of dark matter to visible matter in a galaxy. Galaxies with a higher proportion of dark matter tend to have more stable bars, while those with less dark matter are more likely to experience bar dissolution. This finding highlights the importance of dark matter in shaping the visible universe, even though it remains invisible to direct observation. Simulations have also provided insights into the ways bars interact with spiral arms and other galactic structures. By tracking the movement of stars and gas over time, researchers can observe how bars drive the formation of spiral arms, create resonances that amplify their effects, and even trigger the collapse of gas clouds to form new stars. These models are crucial for understanding the intricate interplay of forces that governs galactic dynamics. The study of galactic bars is not limited to professional astronomers. Citizen science projects, such as Galaxy Zoo, have enlisted the help of amateur astronomers to classify galaxies and identify bars. These efforts have generated vast datasets that researchers can use to study bar properties across a wide range of galaxies. Citizen scientists have made significant contributions to the field, highlighting the importance of public engagement in advancing our understanding of the universe. In many ways, galactic bars represent a microcosm of the broader universe. They illustrate the interconnectedness of cosmic phenomena, from the smallest scales of star formation to the largest structures of galaxy clusters. By studying bars, we gain insights into the fundamental processes that shape the cosmos, deepening our appreciation for the beauty and complexity of the universe. The mysteries of galactic bars continue to captivate astronomers and inspire new questions. How do bars interact with other cosmic structures, such as galaxy halos and intergalactic filaments? What role do bars play in the cosmic web, the vast network of galaxies and dark matter that forms the backbone of the universe? And how can the study of bars help us understand the origins of the universe itself? These questions remind us that the journey of discovery is never complete. As we explore the mysteries of galactic bars, we are not just learning about distant objects in the night sky, we are uncovering the story of our own cosmic origins, piece by piece. The more we learn, the more we realize how much remains to be discovered, ensuring that the study of galactic bars will remain a vibrant and exciting field for generations to come. The deeper we delve into the mysteries of galactic bars, the more we uncover about their role in shaping the cosmos. Galactic bars are not merely static structures. They are dynamic, ever-evolving entities that respond to a galaxy's internal and external conditions. Their interactions with other components of galaxies, such as spiral arms, gas clouds, and dark matter halos, reveal complex feedback mechanisms that drive the evolution of these fascinating systems. One area of ongoing research focuses on the influence of galactic bars on metallicity gradients within galaxies. Metallicity refers to the abundance of elements heavier than helium, which are produced in the cores of stars and distributed through supernova explosions and stellar winds. Typically, the central regions of galaxies have higher metallicities than their outer edges, a trend known as a metallicity gradient. However, the presence of a bar can disrupt this gradient by redistributing gas and stars across the galaxy. Bars drive turbulent flows of gas that mix material from the inner and outer regions of a galaxy, flattening the metallicity gradient. This process not only affects the chemical composition of the galaxy but also provides insights into the timescales over which bars influence galactic evolution. Observing these changes in metallicity gradients allows astronomers to estimate how long a bar has been active and how it has shaped the galaxy's history. Additionally, galactic bars play a critical role in regulating star formation across their host galaxies. By funneling gas toward the center, bars can trigger intense bursts of star formation in the galactic nucleus. This phenomenon, often referred to as a starburst, can transform the central regions of a galaxy into a vibrant, high-energy environment teeming with newly formed stars. These bursts of activity can last for tens of millions of years, creating stellar populations that stand out in both brightness and composition. Interestingly, while bars can enhance star formation in the nucleus, they may also suppress it in the outer regions of the galaxy. By redistributing gas toward the center, bars deplete the outer disk of the material needed for star formation. This dual effect, enhancing activity in the center while quenching it in the outskirts, highlights the profound impact bars have on the spatial distribution of star formation within galaxies. The relationship between galactic bars and dark matter is another area of active exploration. Dark matter, which makes up about 85% of the matter in the universe, does not emit or absorb light and is therefore invisible to telescopes. Its presence is inferred from its gravitational effects on visible matter, such as stars and gas. In barred galaxies, the interaction between the bar and the surrounding dark matter halo can significantly influence the bar's evolution. For instance, simulations suggest that the density of the dark matter halo can affect the bar's strength and longevity. A dense halo can absorb angular momentum from the bar, stabilizing it and preventing its dissolution. Conversely, a less dense halo may allow the bar to weaken over time. These findings underscore the importance of dark matter in shaping not only individual galaxies but also the broader structure of the universe. Moreover, the study of galactic bars has implications for our understanding of galaxy morphology and classification. Bars are a defining feature of many spiral galaxies, which are categorized based on their appearance. The presence or absence of a bar, as well as its size and strength, plays a key role in determining a galaxy's classification within the Hubble sequence, a system developed by Edwin Hubble to categorize galaxies. Barred spiral galaxies, designated as SB in the Hubble sequence, exhibit a wide range of properties. Some have prominent, well-defined bars that dominate their central regions, while others have weaker, more subtle bars that blend into the surrounding disk. The diversity of barred galaxies provides valuable insights into the processes that drive their formation and evolution, as well as the environmental factors that influence their appearance. As we continue to study galactic bars, new technologies and observational techniques are opening up exciting avenues for discovery. The advent of next-generation telescopes, such as the James Webb Space Telescope, JWST, and the Vera-C, Rubin Observatory, promises to revolutionize our understanding of these structures. With their unprecedented sensitivity and resolution, these instruments will allow astronomers to observe bars in greater detail than ever before, uncovering features that were previously invisible. For example, JWST's ability to observe in the infrared spectrum is particularly valuable for studying bars in dusty galaxies, where optical light is obscured by interstellar dust. Infrared observations can penetrate this dust, revealing the hidden structures and dynamics of the bar. Similarly, the Rubin Observatory's wide-field surveys will provide a comprehensive view of barred galaxies across the universe, enabling researchers to study their properties on a statistical scale. The potential for discovery extends beyond individual galaxies to the broader context of cosmic evolution. By studying the distribution and characteristics of bars and galaxies across different epochs, astronomers can trace the history of bar formation and its relationship to the evolution of the universe. These studies will help answer fundamental questions about the role of bars in shaping the cosmic web, the large-scale structure of galaxies and dark matter that permeates the universe. In addition to advancing our scientific understanding, the study of galactic bars has a profound philosophical dimension. These structures, with their intricate patterns and dynamic behavior, remind us of the beauty and complexity of the cosmos. They challenge us to think about the forces that govern the universe and our place within it, inspiring a sense of wonder and curiosity that drives the pursuit of knowledge. As we unravel the mysteries of galactic bars, we are reminded of the interconnectedness of all things in the universe. The same forces that shape these structures, gravity, angular momentum, and the flow of matter, also govern the formation of stars, planets, and even life itself. By studying bars, we gain a deeper appreciation for the intricate web of relationships that binds the cosmos together, from the smallest particles to the largest galaxies. Ultimately, the study of galactic bars is a testament to the power of human curiosity and ingenuity. It is a journey of discovery that takes us to the farthest reaches of the universe, revealing the secrets of its formation and evolution. And while there is still much to learn, each new discovery brings us closer to understanding the profound and awe-inspiring beauty of the cosmos. The study of galactic bars has uncovered yet another fascinating layer of complexity in their interaction with surrounding cosmic phenomena, their influence on galactic mergers and interactions. When galaxies interact or merge, their gravitational forces create tidal disruptions that can significantly alter their structures. Bars play a pivotal role in these events, acting as conduits for energy and material redistribution. During a galactic interaction, the gravitational pull between the two galaxies can strengthen or even induce the formation of a bar in one or both systems. This new or enhanced bar structure accelerates the transfer of gas and stars within the galaxy, often funneling vast amounts of material toward the nucleus. This, in turn, fuels dramatic bursts of star formation and activates the supermassive black hole at the galaxy's center, resulting in the phenomenon known as an active galactic nucleus, AGN. Active galactic nuclei, some of the brightest objects in the universe, are powered by the accretion of material onto supermassive black holes. The energy released during this process can outshine the entire galaxy, producing jets and outflows that impact the surrounding intergalactic medium. Bars serve as the structural highways that enable these dynamic processes by transporting material efficiently and sustaining the activity of AGNs over time. Furthermore, galactic bars have implications for the formation of rings within galaxies. Observational evidence suggests that bars are directly linked to the creation of rings, both inner and outer, through their gravitational influence. Rings are regions of enhanced star formation that often appear as circular or elliptical features around the bar. They are formed when gas clouds are funneled into specific orbits by the bar's gravitational forces, compressing the gas and triggering the birth of new stars. The process of ring formation varies depending on the bar's strength and pattern speed. Inner rings, located near the bar, are typically more tightly bound and may evolve over relatively short timescales. Outer rings, on the other hand, are often associated with the resonance regions of the bar and can take billions of years to fully develop. The interplay between bars and rings showcases the incredible ability of galaxies to self-organize under the influence of gravity and angular momentum. Another key area of research is the lifespan and eventual fate of galactic bars. While bars are long-lived structures, they are not eternal. Over time, bars can weaken and dissolve due to internal and external processes. For instance, the exchange of angular momentum between the bar, the galactic disk, and the dark matter halo can lead to the gradual slowing and elongation of the bar, eventually causing it to fade into the background of the galaxy's disk. Environmental factors, such as interactions with other galaxies or the accretion of external material, can also disrupt bars. These events can introduce turbulence and asymmetry into the galaxy, undermining the stability of the bar. The dissolution of a bar marks a significant transition in the galaxy's evolutionary path, often resulting in a more featureless, elliptical-like structure. Despite their eventual demise, the legacy of galactic bars endures in the form of the structures and dynamics they leave behind. The central bulges they help shape, the metallicity gradients they alter, and the stellar populations they create all bear the imprint of the bar's influence. By studying these remnants, astronomers can reconstruct the history of a galaxy and gain insights into the broader processes that govern the evolution of the cosmos. In the search for a deeper understanding of galactic bars, astronomers have turned to computational simulations and advanced modeling techniques. These tools allow researchers to recreate the conditions under which bars form and evolve, testing hypotheses and exploring scenarios that are difficult to observe directly. Simulations provide a virtual laboratory where scientists can manipulate variables such as gas density, dark matter distribution, and interaction history to observe how bars respond. One of the most exciting developments in this field is the use of machine learning and artificial intelligence, AI, to analyze observational data and simulation results. AI algorithms can identify patterns and correlations that might be overlooked by human observers, offering new insights into the behavior of bars. For example, machine learning has been used to classify barred and unbarred galaxies in large astronomical surveys, streamlining the process of studying these systems on a statistical scale. The potential applications of AI extend beyond classification. By analyzing the properties of galactic bars across different epochs, machine learning algorithms can identify trends and anomalies that shed light on the underlying physics of bar formation. These insights, in turn, can inform the design of future observational campaigns and guide the development of more sophisticated simulations. The study of galactic bars is not just a scientific endeavor, it is also a deeply human pursuit, driven by our innate curiosity and desire to understand the universe. These structures, with their intricate patterns and dynamic behavior, offer a window into the forces that shape the cosmos. They remind us of the interconnectedness of all things, from the smallest particles to the largest galactic structures, and inspire a sense of wonder that transcends the boundaries of science. As we continue to explore the mysteries of galactic bars, we are reminded of the profound beauty and complexity of the universe. Each discovery brings us closer to understanding not only the galaxies we observe but also the broader principles that govern the cosmos. The journey of discovery is far from over, and the next generation of astronomers, armed with powerful new tools and technologies, will undoubtedly uncover even more about these enigmatic structures. And so, the story of galactic bars continues to unfold, a story of dynamic forces, intricate patterns, and the relentless quest to understand the universe we call home. Galactic bars are more than just features of a galaxy's architecture. They are gateways to understanding the broader cosmic environment and the profound relationships between galaxies and the universe. One of the most compelling aspects of studying bars lies in their ability to bridge our knowledge between local and large-scale cosmic structures. These phenomena are instrumental in revealing the interplay between galaxies and the cosmic web, the vast network of filaments and voids that connect the universe on grand scales. Through their dynamic interactions, galactic bars act as catalysts for redistributing angular momentum within the galaxy. This redistribution has a ripple effect that influences not only the structure of the galaxy itself but also its relationship with its surroundings. Bars help regulate how galaxies exchange material with the intergalactic medium, impacting the rates of gas accretion and outflow. These processes play a crucial role in shaping the evolution of galaxies over billions of years. Recent studies suggest that bars may also have a hand in quenching star formation under specific conditions. Quenching occurs when a galaxy exhausts or ejects its gas reservoir, halting the birth of new stars. Bars can drive gas toward the central regions of a galaxy so efficiently that the central black hole's activity may heat or expel the surrounding gas. This process effectively removes the fuel required for star formation, leading to a galaxy transitioning from a blue, star-forming state to a red, quiescent one. Moreover, bars are critical tools for probing the dark matter distribution within galaxies. Since bars are highly sensitive to gravitational forces, their rotation and structure can provide indirect evidence about the dark matter halo enveloping the galaxy. Observational data comparing the bars' pattern, speed, and strength to theoretical models have been used to infer the mass and density profile of dark matter halos. These insights contribute to our understanding of the elusive dark matter, which makes up a significant portion of the universe's mass but remains undetectable through conventional means. Looking beyond individual galaxies, bars also help us piece together the history of galaxy clustering and cosmic epochs. As galaxies interact within clusters, their bars undergo various transformations influenced by tidal forces and mergers. By studying the characteristics of bars in different cosmic environments, such as isolated galaxies, galaxy pairs, and dense clusters, astronomers can reconstruct the environmental conditions that shape these systems. An intriguing connection has been proposed between bars and cosmic evolution over time. Observations have shown that bars were less common in the earlier universe, approximately 6 to 8 billion years ago, than they are today. This suggests that the mechanisms behind bar formation, such as disk stability and the availability of cold gas, have evolved alongside the universe's expansion. Understanding how and why bars became more prevalent provides valuable clues about the changing dynamics of galaxies in different epochs. The advent of cutting-edge telescopes like the James Webb Space Telescope, JWST, has opened new frontiers in the study of galactic bars. With its unparalleled ability to peer into the distant universe, JWST is uncovering bars in galaxies from billions of years ago, offering a glimpse into their early formation stages. These observations are revealing the conditions under which bars first emerged and how they influenced galaxy evolution during the universe's infancy. JWST's high-resolution imaging also allows researchers to observe the fine details of star formation, gas flows, and dust distribution within bars. These insights are critical for testing theoretical models and understanding the physical processes driving bar dynamics. Combined with spectroscopic data, astronomers can investigate the chemical composition of stars and gas in barred regions, shedding light on how these structures enrich galaxies with heavier elements over time. The study of galactic bars also connects to the field of cosmology, where understanding the distribution of matter and energy on large scales is essential. Bars serve as natural laboratories for testing theories about the universe's composition, including the role of dark energy in driving cosmic acceleration. By studying how bars evolve and interact with their environments, researchers can refine models of galaxy formation and growth, which are integral to our broader understanding of the cosmos. In addition to advancing scientific knowledge, galactic bars capture the imagination with their striking visual beauty and dynamic complexity. From their sweeping spiral arms to their intricate internal structures, they represent nature's artistry on a cosmic scale. For amateur astronomers and casual stargazers, barred spiral galaxies like NGC 1300 and Messier 83 offer mesmerizing views that invite curiosity and inspire a deeper appreciation for the universe. As we continue to explore the mysteries of galactic bars, the quest to understand these structures becomes a testament to human ingenuity and perseverance. Each discovery builds upon centuries of astronomical inquiry, from early observations with simple telescopes to today's sophisticated multi-wavelength studies. The journey is far from over, as new technologies and ideas promise to unveil even more about these enigmatic features. The narrative of galactic bars exemplifies the profound connections between seemingly disparate elements of the universe. They are not just features of isolated galaxies but active participants in a cosmic dance that shapes the fate of galaxies, clusters, and beyond. Their study bridges disciplines, from astrophysics to cosmology, demonstrating how interconnected the universe truly is. Ultimately, the investigation of galactic bars reminds us of the boundless mysteries that await discovery. As we look deeper into the cosmos, each bar becomes a symbol of the universe's dynamic nature, a testament to its capacity for transformation, complexity, and wonder. The story of galactic bars is a story of motion, interaction, and evolution, echoing the eternal dance of the cosmos itself. The influence of galactic bars extends to some of the most enigmatic questions in modern astrophysics, particularly the role they play in galactic self-regulation and feedback mechanisms. Self-regulation refers to a galaxy's ability to balance competing forces, star formation, gas inflow, and outflow, to maintain a stable structure over billions of years. Bars, as dynamic and adaptive structures, serve as key players in this balancing act. One way bars contribute to self-regulation is by triggering waves of star formation. As gas is funneled along the bar's length and compressed in its orbit, this dense material ignites bursts of star formation. These new stars, in turn, emit powerful stellar winds and radiation, injecting energy back into the surrounding medium. This feedback can either enhance or suppress subsequent star formation depending on the intensity and distribution of the energy. Additionally, the funneling of gas into the central regions of a barred galaxy often leads to the formation of a nuclear starburst or a circumnuclear ring, dense regions teeming with star-forming activity. These regions are critical for understanding how galaxies grow and evolve over time. Nuclear starbursts can consume the available gas reservoir rapidly, effectively quenching star formation in the galaxy's core. On the other hand, circumnuclear rings provide a steady supply of gas for star formation, sustaining activity over much longer timescales. Bars also help regulate chemical enrichment in galaxies. As gas flows inward along the bar, it brings with it a mix of primordial material and enriched elements from outer regions. This mixing process homogenizes the galaxy's chemical composition, reducing radial metallicity gradients and ensuring a more even distribution of elements. By transporting heavy elements produced by dying stars, bars enrich future generations of stars, leaving a lasting imprint on the galaxy's evolutionary path. In some cases, bars may also play a role in creating stellar populations with unique properties. For instance, certain clusters of stars found in the cores of barred galaxies exhibit unusually high metallicities or peculiar kinematics. These anomalies are thought to result from the bar's ability to concentrate material and create an environment where unusual star formation events can occur. Studying these stellar populations provides a window into the past activity of the bar and the galaxy as a whole. Another remarkable aspect of galactic bars is their relationship with galaxy morphology and classification. The presence or absence of a bar can significantly influence how a galaxy is categorized. Barred spiral galaxies are a distinct subset of the broader spiral galaxy classification and are often denoted with the letter B in the Hubble sequence, e.g., SB for barred spirals. Observations suggest that bars are more prevalent in late-type spiral galaxies, which tend to have higher gas content and more active star formation. Interestingly, the proportion of barred galaxies appears to vary depending on the environment. Galaxies in dense clusters are less likely to host bars, possibly due to the disruptive effects of frequent interactions and the stripping of gas. In contrast, isolated galaxies are more likely to develop and sustain bars, as they experience fewer external disturbances. This environmental dependence highlights the delicate balance of forces required for bar formation and stability. One of the most exciting frontiers in the study of bars involves their connection to cosmic gas flows and the intergalactic medium, IgM. Bars are thought to influence how galaxies acquire fresh gas from their surroundings, replenishing their star-forming reservoirs. In some cases, bars may act as cosmic funnels, channeling material from large-scale gas streams directly into the galaxy. This process ties the internal dynamics of galaxies to the larger-scale structures of the universe, emphasizing the interconnected nature of cosmic evolution. On the flip side, bars can also expel gas from galaxies through outflows driven by stellar feedback or active galactic nuclei, AGN. These outflows contribute to the enrichment of the IgM, seeding it with heavy elements and energy. Understanding how bars mediate these inflows and outflows is essential for piecing together the puzzle of galaxy growth and decline. Another area of active research focuses on the triggers of bar formation. While the internal instabilities of a galactic disk are the primary mechanism, external factors such as minor mergers and tidal interactions can also induce bar formation. Simulations suggest that even small perturbations, like the gravitational influence of a passing galaxy, can create the conditions necessary for a bar to emerge. These events underscore the role of cosmic interactions in shaping galactic structures. Interestingly, some barred galaxies host double bars, where a smaller, secondary bar resides within the primary bar. These nested structures, also known as inner bars, are rare but provide valuable insights into the multi-scale dynamics of galaxies. Inner bars are thought to rotate independently of their larger counterparts, creating complex patterns of gas and star motion. Studying double-barred galaxies offers a unique opportunity to understand how nested gravitational systems operate and evolve. In the grand scheme of cosmic history, bars may also serve as markers of galactic maturity. The prevalence of bars in the modern universe, compared to their rarity in earlier epochs, suggests that they are features of dynamically evolved galaxies. As galaxies age and settle into equilibrium, their disks become more susceptible to bar-forming instabilities. This evolutionary trend makes bars valuable tools for reconstructing the timeline of galaxy formation and transformation. Looking ahead, the study of galactic bars will continue to benefit from advancements in technology and methodology. Upcoming telescopes like the Vera C. Rubin Observatory will conduct wide-field surveys of unprecedented depth and resolution, capturing millions of galaxies and their bars across cosmic time. These data sets will enable astronomers to analyze bar formation and evolution on a statistical scale, uncovering trends that were previously invisible. In addition, advances in simulation techniques will allow researchers to model bars with greater precision and complexity. High-resolution simulations that incorporate realistic physics, such as gas cooling, star formation, and feedback, will shed light on the fine details of bar dynamics. These simulations will also help bridge the gap between theoretical predictions and observational data, providing a more complete picture of how bars operate. Galactic bars are not just scientific curiosities. They are cosmic phenomena that resonate with profound philosophical and existential questions. Their study invites us to ponder the forces that govern the universe, the interconnectedness of all matter, and the intricate dance of creation and destruction that defines the cosmos. Bars remind us that even amidst the vastness of space, there are patterns and structures that reflect the order and beauty of nature. As we delve deeper into the mysteries of galactic bars, we uncover not only the secrets of galaxies but also the story of the universe itself. Each bar tells a tale of motion, transformation, and connection, echoing the fundamental principles that govern existence. The quest to understand these structures is a journey of discovery, wonder, and awe, a testament to humanity's enduring curiosity and drive to explore the unknown. The role of galactic bars in shaping the universe goes beyond their immediate structures. They are crucial to understanding how galaxies interact with their surroundings and evolve over billions of years. For example, bars may act as a bridge between isolated galaxies and the cosmic web, influencing the exchange of matter and energy at a galactic scale. This connection underscores the role bars play as facilitators in the grand cosmic symphony, channeling material from vast intergalactic spaces into the dense regions where stars and planets form. One particularly fascinating area of study involves the relationship between galactic bars and supermassive black holes, SMBHs, at the centers of galaxies. Observations reveal that bars are highly efficient at driving gas toward the galactic nucleus, where SMBHs reside. This inflow of material can trigger active galactic nuclei, AGN, activity, where the black hole consumes large amounts of gas and emits intense radiation across the electromagnetic spectrum. Interestingly, the interaction between a bar and its central black hole is not one-sided. Feedback from the AGN, in the form of powerful jets and outflows, can affect the bar's stability and the distribution of gas within the galaxy. This feedback loop creates a dynamic interplay between the bar and the black hole, with profound implications for the galaxy's long-term evolution. Understanding these interactions can help us answer some of the biggest questions in astrophysics, such as how SMBHs grow and how they influence their host galaxies. Moreover, bars are thought to play a critical role in the quenching of star formation, a process that transforms star-forming galaxies into passive, red and dead systems. By funneling gas inward, bars can either consume it through rapid star formation or deposit it into the central regions, where it becomes inaccessible for further star formation. This dual role makes bars both creators and destroyers, capable of shaping the life cycle of a galaxy. In the broader context of cosmic evolution, the formation of bars is linked to the cosmic epoch of disk settling. During the early universe, galaxies were turbulent, irregular, and dominated by violent mergers. As the universe aged, galaxies began to settle into more stable disk structures, setting the stage for bar formation. The appearance of bars marks a critical phase in a galaxy's life cycle, signifying a transition from chaotic, merger-driven growth to a more stable, internally driven evolution. Bars also offer clues about the dark matter halos that envelop galaxies. While dark matter is invisible, its gravitational influence shapes the dynamics of galaxies, including the formation and evolution of bars. Simulations suggest that the properties of a bar, its length, strength, and rotation speed, are influenced by the density and distribution of dark matter in the galaxy's halo. By studying bars, astronomers can indirectly probe the elusive nature of dark matter and its role in cosmic structure formation. Another intriguing aspect of bars is their potential role in explaining anomalies in galaxy rotation curves. Observations of galaxies have shown that their outer regions rotate faster than expected based on visible matter alone, a phenomenon attributed to dark matter. However, some researchers propose that the presence of a bar could influence the dynamics of the disk in ways that mimic or amplify the effects of dark matter. While this idea is still debated, it highlights the complexity of disentangling the various factors that govern galactic motion. In terms of observational techniques, studying galactic bars has become increasingly sophisticated thanks to advances in multi-wavelength astronomy. By observing bars across different wavelengths, from visible light to radio and infrared, astronomers can piece together a comprehensive picture of their composition, dynamics, and impact. For instance, infrared observations are particularly valuable for studying the dust and gas within bars, while radio telescopes can trace the distribution of neutral hydrogen, a key component of the interstellar medium. Another powerful tool is integral field spectroscopy, IFS, which allows astronomers to map the motions of stars and gas within a galaxy in 3 dimensions. By combining IFS data with advanced simulations, researchers can create detailed models of bar dynamics, shedding light on their formation mechanisms and long-term evolution. The discovery of galactic bars in distant galaxies has also opened new windows into the early universe. Thanks to powerful telescopes like the James Webb Space Telescope, JWST, astronomers are now able to detect bars in galaxies that existed just a few billion years after the Big Bang. These early bars provide valuable insights into how galaxies evolved during their formative stages and how the conditions of the young universe influenced bar formation. While much has been learned about galactic bars, many questions remain unanswered. For example, why do some galaxies form bars while others do not? Are bars a universal phase in the life of all disk galaxies? Or are they a product of specific conditions? How do bars influence the ultimate fate of their host galaxies? Do they prolong their lifespans or hasten their decline? These mysteries continue to drive research in this fascinating field. What makes galactic bars particularly compelling is their role as cosmic laboratories. By studying bars, we can explore fundamental physical processes such as angular momentum transfer, fluid dynamics, and gravitational instabilities. These processes are not limited to galaxies. They are universal phenomena that occur on all scales, from planetary systems to galaxy clusters. As such, the study of bars has far-reaching implications for our understanding of the universe. In a sense, galactic bars are a testament to the intricate balance of forces that governs the cosmos. They are the result of a delicate interplay between gravity, motion, and matter, and their existence underscores the interconnectedness of all things in the universe. Each bar is a dynamic structure, constantly evolving and interacting with its surroundings, a microcosm of the larger cosmic story. As we look to the future, the study of galactic bars promises to yield even more profound insights. With next-generation observatories and advanced simulations, we are poised to uncover the secrets of these fascinating structures and their role in shaping the universe. In doing so, we will not only deepen our understanding of galaxies but also gain a greater appreciation for the beauty and complexity of the cosmos. The mysteries of galactic bars remind us that even the most familiar structures in the universe hold surprises waiting to be discovered. They are a symbol of the endless curiosity and wonder that drives us to explore, learn, and uncover the hidden truths of the cosmos. And as we continue this journey, we can be certain that galactic bars will remain a rich and rewarding subject of study for generations to come. The study of galactic bars offers a window into the complex choreography of matter, energy, and gravity that defines the universe. These structures are more than just architectural features of galaxies. They are key players in the dynamic processes that govern galactic evolution. As researchers dive deeper into their mysteries, the scope of what bars reveal about the cosmos expands, making them an ever more fascinating subject of inquiry. One particularly intriguing aspect of galactic bars is their relationship with spiral arms. Observations and simulations suggest that bars and spiral arms are often intricately linked, with the bar acting as a kind of generator for spiral structure. The gravitational forces exerted by a bar can trigger density waves in the surrounding disk, creating the iconic spiral pattern seen in many galaxies. These spirals are not static structures. They are dynamic, continually influenced by the bar's rotation and the flow of material within the galaxy. The interplay between bars and spiral arms is a topic of intense study because it sheds light on how galaxies redistribute their mass and angular momentum over time. This redistribution is crucial for understanding the long-term stability of galaxies. For example, the bar can channel gas inward, fueling central star formation, while simultaneously pushing stars outward, creating a more extended galactic disk. This dual action highlights the bar's role as both a driver of change and a stabilizing force within the galaxy. Another captivating aspect is the lifespan of galactic bars. While bars are relatively stable structures, they are not permanent. Over time, they can dissolve or weaken due to interactions with other galaxies, changes in the galaxy's mass distribution, or the influence of dark matter halos. The dissolution of a bar marks a significant phase in a galaxy's life, often leading to a more quiescent state. Understanding the conditions that lead to the formation and dissolution of bars is a major focus of current research, as it provides insights into the broader cycles of galactic evolution. Galactic bars also play a significant role in the context of environmental influences on galaxies. Galaxies do not exist in isolation. They are part of larger structures like galaxy groups and clusters. The gravitational interactions between galaxies in these environments can influence the formation and evolution of bars. For instance, a close encounter with another galaxy can trigger or enhance a bar, as the gravitational forces destabilize the disk and create the conditions for bar formation. Conversely, such interactions can also disrupt an existing bar, leading to its premature dissolution. One of the most exciting frontiers in the study of galactic bars is their potential to act as probes of dark matter. While dark matter itself is invisible, its gravitational influence shapes the dynamics of galaxies. By studying the motion of stars and gas in barred galaxies, astronomers can infer the distribution of dark matter in the galactic halo. This research has already provided valuable constraints on the nature of dark matter and its role in cosmic structure formation. The study of bars also intersects with the field of galactic archaeology. By analyzing the chemical composition and motion of stars in and around the bar, researchers can reconstruct the history of the galaxy. For example, stars formed in the bar tend to have distinct chemical signatures compared to those in the spiral arms or outer disk. These differences provide clues about the galaxy's past, including its star formation history, interactions with other galaxies, and the evolution of its central black hole. Looking to the future, the study of galactic bars is set to benefit from a wave of technological advancements. Next-generation telescopes like the Extremely Large Telescope, (ELT), and the Square Kilometre Array, (SKA), will provide unprecedented detail about bars in nearby and distant galaxies. These instruments will allow astronomers to study the smallest details of bar dynamics, from the motion of individual stars to the flow of gas within the bar. Meanwhile, advancements in computational astrophysics are enabling researchers to create more sophisticated simulations of barred galaxies. These simulations are critical for testing theories about bar formation, evolution, and dissolution. By comparing simulation results with observations, scientists can refine their models and gain a deeper understanding of the physical processes at play. Despite these advancements, many questions about galactic bars remain unanswered. For instance, what determines the exact timing of bar formation in a galaxy's life cycle? Why do some galaxies develop strong, prominent bars while others have faint or no bars at all? How do the properties of a bar change as the galaxy evolves? These questions are not just academic, they touch on fundamental aspects of how the universe works. Galactic bars are also a reminder of the interconnected nature of cosmic phenomena. Their study does not exist in isolation but intersects with fields like star formation, black hole physics, dark matter research, and galaxy evolution. This interconnectedness makes bars a microcosm of the larger universe, a single thread in the vast tapestry of cosmic phenomena. The mystery of galactic bars lies in their ability to simultaneously reveal and obscure the workings of the universe. They are both familiar and enigmatic, offering glimpses of cosmic order while hinting at deeper, unresolved questions. As our tools and techniques continue to improve, the secrets of these structures will gradually come to light, adding yet another layer to our understanding of the cosmos. Galactic bars are more than just features of galaxies. They are key to unraveling the story of the universe. They remind us that even in the seemingly ordinary, there is a wealth of mystery waiting to be explored. And as we continue to study these fascinating structures, we are reminded of the boundless curiosity that drives us to explore the unknown. The role of galactic bars in shaping the universe cannot be overstated. These structures, while common in many galaxies, serve as laboratories for understanding fundamental principles of astrophysics. Their study not only deepens our understanding of galaxies but also informs us about the larger cosmic environment in which they reside. To continue unraveling the mysteries of galactic bars, let's explore the intricate processes they set into motion and the unanswered questions that drive modern astrophysics. Galactic bars are significant engines of angular momentum transfer, which profoundly affects the distribution of mass within a galaxy. Angular momentum is a measure of rotational motion, and its redistribution is a central process in galactic evolution. Bars act as conduits, funneling angular momentum from the inner regions of a galaxy to the outer disk. This redistribution drives the migration of stars, alters the structure of spiral arms, and changes the overall dynamics of the galactic disk. Understanding this process requires precise measurements of stellar velocities, which are made possible through modern spectroscopic surveys like those conducted by the Gaia spacecraft. These mechanisms are not just theoretical. Observations of barred galaxies show clear evidence of radial migration, where stars are displaced from their birthplaces and move to different parts of the galaxy. This migration has profound implications for the galaxy's chemical composition. For instance, older stars formed closer to the galactic core are typically metal-rich due to the abundance of heavier elements in the dense, star-forming regions. As these stars migrate outward due to the bar's influence, they create a more chemically diverse outer disk. This redistribution helps astronomers reconstruct the galaxy's star formation history, offering a unique lens through which to view its evolution. One of the most visually striking features of galactic bars is their ability to generate ring structures within galaxies. Rings often form around the ends of bars, where gas accumulates due to gravitational resonance. These rings can host intense star formation, resulting in regions that are often brighter and more dynamic than the surrounding areas. Rings are classified based on their location relative to the bar. Inner rings, outer rings, and nuclear rings are common categorizations. Each type of ring provides clues about the dynamics of the galaxy, including the bar's influence on the motion of gas and stars. Nuclear rings, in particular, are hotspots for star formation. Found in the central regions of barred galaxies, these rings are dense concentrations of gas and dust that spiral inward due to the bar's gravitational pull. The gas in these regions undergoes compression, leading to the rapid formation of new stars. These stars can, in turn, influence the bar by altering its gravitational potential. This feedback loop between the bar and star formation is a key area of study, as it highlights the interconnected nature of galactic processes. The influence of bars extends beyond the visible disk of a galaxy. Recent studies have revealed that bars can interact with the halo of dark matter surrounding a galaxy. This interaction is subtle but significant. The gravitational pull of the bar can create distortions in the dark matter halo, which in turn affects the motion of stars and gas in the disk. By studying these interactions, astronomers hope to gain insights into the nature of dark matter, one of the most enigmatic components of the universe. Galactic bars are also deeply tied to the evolution of supermassive black holes, SMBHs, at the centers of galaxies. Bars drive gas inward toward the galactic core, where it can be accreted by the black hole. This accretion process fuels the growth of the black hole and powers phenomena like active galactic nuclei, AGN, and quasars. The relationship between bars and black holes is a complex one, as the inflow of gas can also lead to starbursts that compete with the black hole for available material. Understanding this balance is crucial for developing a comprehensive model of galaxy evolution. Interestingly, not all bars are the same. Some galaxies exhibit strong bars, characterized by well-defined, elongated structures, while others have weak bars that are less prominent and more difficult to detect. The strength of a bar depends on a variety of factors, including the galaxy's mass distribution, the composition of its disk, and its interaction history. For example, a recent collision with another galaxy can strengthen an existing bar or even trigger the formation of a new one. On the other hand, a bar may weaken and dissolve if the galaxy undergoes significant internal changes, such as the redistribution of its dark matter halo. The diversity of barred galaxies also extends to their morphological classification. The Hubble sequence, a system for categorizing galaxies, includes a distinct class for barred spiral galaxies, denoted as SB galaxies. These galaxies are further divided into subcategories based on the prominence of their spiral arms and the size of their bars. This classification system, while useful, does not capture the full complexity of barred galaxies. Modern surveys are expanding our understanding by uncovering a wide range of bar morphologies, including boxy and peanut-shaped bars, which are thought to result from vertical instabilities in the disk. The future of galactic bar research lies in multi-wavelength observations. While optical telescopes provide detailed images of stellar structures, radio and infrared observations are essential for studying the gas and dust within bars. For instance, radio observations can trace the motion of hydrogen gas, while infrared observations reveal the distribution of cooler stars and interstellar dust. Combining these data across different wavelengths offers a more complete picture of how bars influence their host galaxies. One of the most exciting developments in this field is the use of machine learning and artificial intelligence to analyze large datasets. With the advent of surveys like the Sloan Digital Sky Survey (SDSS) and the Vera-C, Rubin Observatory's Legacy Survey of Space and Time (LSST), astronomers now have access to millions of galaxy images. Machine learning algorithms can classify these galaxies, identify bars, and even detect subtle features that might be missed by human observers. This technology is revolutionizing the study of galactic bars, allowing researchers to tackle questions that were previously out of reach. Despite the progress made, many mysteries about galactic bars remain unsolved. For example, what triggers the initial formation of a bar? While it is known that certain conditions, like a high disk-to-halo mass ratio, can promote bar formation, the exact mechanisms are still under investigation. Additionally, the role of bars in the broader cosmic context is not fully understood. How do bars influence the large-scale structure of the universe? Do they play a role in the formation of galaxy clusters and superclusters? These questions are at the forefront of modern astrophysics. As we continue to probe the universe, galactic bars serve as a reminder of the complexity and beauty of cosmic structures. They are both familiar and enigmatic, offering a wealth of information about the forces that shape galaxies and the universe as a whole. By studying these structures, we not only deepen our understanding of the cosmos but also gain a greater appreciation for the intricate interplay of matter, energy, and time that defines our place in the universe. The study of galactic bars opens the door to deeper questions about the fabric of the universe. These structures are not isolated phenomena. They interact with their surroundings in ways that reveal the underlying principles of cosmic evolution. From their formation to their eventual dissolution, bars are dynamic entities that encapsulate the complexity of astrophysical processes. One area of active research is the lifespan of galactic bars. While bars are relatively stable over millions of years, they are not permanent features. Observations and simulations suggest that bars can weaken or dissolve over time due to a variety of factors. One such factor is the redistribution of angular momentum, particularly when the outer disk absorbs too much angular momentum from the bar. This process can effectively reduce the bar's strength, and in some cases, cause it to disappear entirely. The timescale for this dissolution varies widely, depending on the galaxy's mass, composition, and interaction history. Galaxy mergers and gravitational interactions with neighboring galaxies can also disrupt bars. When two galaxies collide or pass close to each other, the resulting tidal forces can distort the structure of the disks. These interactions may either strengthen an existing bar or lead to its destruction. Understanding these interactions is crucial for piecing together the history of galaxies and the role of bars in shaping their evolution. Advanced simulations, coupled with observational data, are helping astronomers model these complex scenarios with increasing accuracy. Another key question concerns the feedback loops generated by bars. Bars channel gas toward the central regions of galaxies, fueling star formation and possibly triggering the growth of the central black hole. But this process is not unidirectional. The energy released by newly formed stars, along with the activity of the central black hole, can generate outflows that push gas outward, counteracting the inward flow caused by the bar. These competing processes create a delicate balance that determines the overall structure and behavior of the galaxy. Studying this interplay offers valuable insights into the mechanisms that regulate galaxy growth. Moreover, bars are essential for understanding the formation and evolution of spiral arms. In many barred galaxies, the bar serves as the anchor for spiral structures, with the arms extending outward from the ends of the bar. These spiral arms are not static features. They are constantly reshaped by the motion of stars and gas within the disk. Bars influence this motion by generating density waves, which propagate through the disk and create the appearance of spirals. The relationship between bars and spiral arms is a rich field of study that bridges the gap between small-scale processes and large-scale galactic structure. The chemical evolution of galaxies is another area where bars play a pivotal role. By driving the radial migration of stars and gas, bars create gradients in the distribution of chemical elements. These gradients provide a record of the galaxy's star formation history, as well as its interactions with the surrounding environment. Observations of these gradients, combined with theoretical models, help astronomers reconstruct the life cycle of galaxies and the role of bars in shaping their chemical diversity. As we study bars, we are also confronted with the question of their cosmological significance. Bars are not merely features of individual galaxies. They are part of a larger cosmic web that connects galaxies across vast distances. By influencing the distribution of matter within galaxies, bars may play a role in the formation of larger structures, such as galaxy groups and clusters. Understanding this connection requires a multi-scale approach that combines observations of individual galaxies with simulations of the large-scale universe. The future of galactic bar research is bright, thanks to advancements in technology and methodology. Next-generation telescopes, such as the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory, are providing unprecedented views of galaxies across the universe. These instruments allow astronomers to study bars in greater detail, from their internal dynamics to their interactions with the larger cosmic environment. Coupled with advancements in computational astrophysics, these tools are enabling a new era of discovery. One particularly exciting avenue of research is the use of high-resolution simulations to study bar formation and evolution. These simulations are computationally intensive, but they provide a detailed view of the processes that shape bars over time. By comparing these simulations with observations, astronomers can test theoretical models and refine our understanding of the physics underlying bar dynamics. This iterative process of observation and modeling is at the heart of modern astrophysics. The study of bars also has implications for understanding dark matter, one of the most mysterious components of the universe. Dark matter does not interact with light, making it invisible to telescopes. However, its gravitational effects can be observed in the motion of stars and gas within galaxies. Bars provide a unique laboratory for studying these effects, as their interactions with the dark matter halo can reveal important clues about its properties. By examining the shape and dynamics of bars, astronomers can gain insights into the distribution and behavior of dark matter, bringing us closer to solving one of the greatest mysteries of modern science. In addition to dark matter, bars may also provide clues about the early universe. Observations of distant galaxies, whose light has traveled billions of years to reach us, show that bars were already present in the early stages of galaxy formation. These early bars offer a glimpse into the conditions of the young universe, including the processes that led to the formation of the first galaxies. By studying these ancient structures, we can piece together the story of how galaxies, and the universe as a whole, evolved over cosmic time. Despite these advancements, many questions remain unanswered. Why do some galaxies develop strong bars while others do not? What determines the length and strength of a bar? How do bars influence the formation of galaxy clusters and the large-scale structure of the universe? These questions drive ongoing research and inspire new generations of astronomers to explore the mysteries of galactic bars. Ultimately, the study of galactic bars is a testament to the complexity and beauty of the universe. These structures, though small in the grand scheme of things, encapsulate the interconnectedness of cosmic processes. By understanding bars, we not only gain insights into the workings of galaxies but also uncover the deeper truths that govern the universe itself. The mysteries of galactic bars extend far beyond their visible structures, touching on some of the most profound questions about the universe. The processes that govern their formation and evolution are interconnected with the mechanisms shaping galaxies, influencing the distribution of stars, gas, and even dark matter across the cosmos. Each discovery about bars opens a new pathway to understanding the universe, often raising more questions than answers. One area where bars remain particularly enigmatic is their connection to galaxy morphology and classification. In the famous Hubble sequence, galaxies are categorized as spiral, elliptical, or irregular, with spirals further divided into barred and unbarred varieties. But why do some spiral galaxies develop prominent bars while others do not? Studies suggest that this distinction may arise from differences in the galaxy's angular momentum, mass distribution, and interaction history. However, the precise factors that determine whether a bar will form, and how long it will last, remain elusive. Environmental factors also play a significant role in the prevalence of bars. Galaxies in dense environments, such as galaxy clusters, are more likely to exhibit bars than those in isolation. This correlation hints at the influence of gravitational interactions and tidal forces, which can trigger the internal instabilities needed for bar formation. However, galaxies in these environments are also subject to processes like ram pressure stripping, which removes gas from their outer regions and can inhibit star formation. Balancing these competing effects is a delicate process that continues to challenge astrophysicists. The study of barred galaxies has also revealed intriguing connections to the overall cosmic structure. Observations show that bars tend to align with the large-scale filaments of the cosmic web, the vast network of dark matter and galaxies that stretches across the universe. This alignment suggests that bars are not merely internal features of galaxies but are influenced by the larger gravitational landscape in which they reside. Understanding these connections requires sophisticated simulations that combine models of galaxy formation with the large-scale dynamics of the universe. Bars also serve as a critical link between galactic dynamics and cosmology. Because they redistribute mass and angular momentum within galaxies, bars play a role in shaping the rotation curves that are used to study dark matter. Observations of these rotation curves often reveal discrepancies that cannot be explained by visible matter alone, pointing to the presence of a dark matter halo. By examining the interactions between bars and these halos, astronomers hope to uncover new insights into the nature and distribution of dark matter. The role of bars in triggering starbursts, intense episodes of star formation, is another area of active research. By funneling gas into the central regions of galaxies, bars can create conditions that lead to rapid star formation. These starbursts can significantly alter the evolution of a galaxy by enriching its chemical composition, producing massive stars, and driving powerful winds that expel gas into the surrounding space. However, not all bars trigger starbursts, leading scientists to investigate the specific conditions under which this phenomenon occurs. Factors such as the amount of available gas, the strength of the bar, and the presence of additional dynamical features like inner rings all play a role in determining whether a bar will ignite a starburst. The interaction between bars and supermassive black holes, SMBHs, at the centers of galaxies is another fascinating area of study. Bars are highly effective at channeling gas toward the galactic nucleus, where it can be accreted by the central black hole. This accretion process powers active galactic nuclei, AGN, which emit tremendous amounts of energy across the electromagnetic spectrum. The relationship between bars and AGN activity has been observed in numerous galaxies, suggesting that bars may act as a trigger mechanism for black hole growth. However, this relationship is not universal, and many barred galaxies show little or no AGN activity. Understanding this disparity is a key goal for researchers seeking to uncover the connection between bars, black holes, and galaxy evolution. The feedback mechanisms associated with AGN further complicate the picture. As gas falls into a supermassive black hole, the energy released can heat or expel the surrounding gas, effectively halting further accretion and star formation in the central regions of the galaxy. This feedback can have far-reaching effects, shaping the structure of the galaxy and even influencing the bar itself. The interplay between bars, starbursts, and AGN feedback represents a delicate balance that determines the long-term evolution of a galaxy. Moving beyond individual galaxies, the study of bars provides insights into the formation and evolution of galaxy clusters and groups. Bars can serve as tracers of past interactions, preserving evidence of mergers and tidal encounters in their shapes and orientations. For example, bars that are unusually long or misaligned with the rest of the galaxy may indicate a history of strong gravitational interactions. By studying these features, astronomers can reconstruct the evolutionary history of galaxies and the environments in which they reside. Bars also play a role in the chemical enrichment of galaxies. As they drive gas toward the center, bars can mix material from different parts of the galaxy, creating a more homogeneous distribution of chemical elements. This mixing process has been observed in the metallicity gradients of barred galaxies, which are typically shallower than those of unbarred galaxies. Understanding how bars influence chemical evolution is essential for interpreting the spectra of distant galaxies and piecing together the history of star formation across the universe. In addition to their physical and chemical effects, bars provide a unique window into the dynamics of dark matter. Observations and simulations suggest that bars interact with the dark matter halo that surrounds a galaxy, exchanging angular momentum and energy. These interactions can influence the shape of the halo, creating deviations from the spherical or elliptical distributions predicted by simple models. By studying the dynamics of bars, astronomers can test theories of dark matter and explore alternative explanations, such as modifications to the laws of gravity. The study of bars is further enriched by multi-wavelength observations, which reveal different aspects of their structure and behavior. Optical images highlight the distribution of stars, while infrared observations penetrate the dust that often obscures the central regions of galaxies. Radio telescopes map the distribution of neutral hydrogen gas, while X-ray observations reveal the hot gas and high-energy processes associated with AGN and starbursts. Combining data from these different wavelengths provides a more complete picture of how bars influence their host galaxies. The advent of next-generation telescopes and instruments promises to revolutionize our understanding of galactic bars. The James Webb Space Telescope, JWST, is already providing unprecedented views of distant galaxies, allowing astronomers to study bars in the early universe. Meanwhile, the Vera C. Rubin Observatory is expected to produce a massive dataset of nearby galaxies, enabling statistical studies of bars across a wide range of environments. These observations, combined with advances in computational modeling, will help answer some of the most pressing questions about the formation and evolution of bars. One of the most exciting frontiers in bar research is the study of high-redshift galaxies. Observations of these galaxies provide a glimpse into the conditions of the early universe, when the first bars were forming. These bars are often smaller and less well-defined than those in nearby galaxies, reflecting the more chaotic environments of their host galaxies. By studying these early bars, astronomers can learn about the processes that shaped the first galaxies and set the stage for the large-scale structure of the universe. As our understanding of galactic bars deepens, it becomes increasingly clear that these structures are not just features of individual galaxies, but are integral to the broader narrative of cosmic evolution. They are the engines driving the redistribution of matter, the catalysts for star formation and black hole growth, and the tracers of past interactions and environmental influences. Through their study, we gain not only a better understanding of galaxies but also new insights into the fundamental forces and processes that govern the universe. The mysteries of galactic bars remind us that even the most familiar features of the cosmos can hold profound secrets. Each discovery about these structures brings us closer to answering the age-old questions of how galaxies form, evolve, and interact with their environment. At the same time, they challenge us to think beyond the boundaries of current knowledge, inspiring new questions and new avenues of exploration. In the ever-expanding quest to understand the universe, galactic bars serve as a powerful reminder of the complexity and beauty of the cosmos. The continued exploration of galactic bars highlights the intricate tapestry of processes shaping the universe. As we delve deeper into their mysteries, it becomes increasingly evident that these structures are key to deciphering broader cosmic phenomena, including galaxy evolution, star formation, and the role of dark matter. One of the unanswered questions surrounding galactic bars concerns their lifespan. While simulations suggest that bars can persist for billions of years, observations indicate that some galaxies transition between barred and unbarred phases. This variability raises intriguing possibilities. Are bars inherently stable structures, or do they dissolve and reform over time due to internal and external influences? To answer this question, researchers are studying the conditions that lead to bar formation and the mechanisms that might cause their dissolution. One possible explanation for the temporary nature of some bars lies in secular evolution, the gradual redistribution of angular momentum and mass within a galaxy over time. Bars are thought to form when internal instabilities cause the stellar orbits in the disk to align in elongated patterns. However, as the bar interacts with the galaxy's dark matter halo, angular momentum is transferred, potentially weakening the bar. Additionally, the accumulation of gas in the central regions can increase the gravitational potential, leading to the destabilization of the bar structure. Understanding these processes is crucial for piecing together the life cycle of bars and their role in shaping galaxies. Another avenue of research focuses on the role of gas and star formation in bar dynamics. While bars are known to funnel gas toward the galactic center, the exact mechanisms governing this process remain unclear. Observations show that gas flows along the bar's length, accumulating in the central regions and triggering bursts of star formation. However, the efficiency of this process depends on factors such as the strength of the bar, the amount of available gas, and the galaxy's overall structure. Simulations are helping to unravel these complexities, providing valuable insights into the interplay between bars, gas dynamics, and star formation. The influence of bars extends beyond individual galaxies, impacting galactic interactions and mergers. When two galaxies interact, their gravitational forces can trigger the formation or enhancement of bars in one or both galaxies. These interactions often lead to the redistribution of mass and angular momentum, creating conditions favorable for bar formation. Conversely, bars can also be disrupted during mergers, particularly if the resulting galaxy is highly irregular. Studying these interactions provides a window into the dynamic processes that shape galaxies over cosmic timescales. Bars also play a role in the chemical evolution of galaxies, acting as conduits for the mixing and redistribution of elements. As gas flows along the bar, it can carry metals from the outer regions to the center, enriching the central regions with heavier elements. This process can be observed in the metallicity gradients of barred galaxies, which are typically flatter than those of unbarred galaxies. By studying these gradients, astronomers can gain insights into the history of star formation and gas flows within galaxies. In addition to their role in star formation and chemical enrichment, bars influence the morphological evolution of galaxies. Over time, the redistribution of mass caused by bars can transform the shape of a galaxy, creating features such as rings, bulges, and even pseudobulges, structures that resemble classical bulges but form through different processes. The distinction between these types of bulges is a topic of ongoing debate, with bars playing a central role in driving their formation. The study of bars also intersects with the quest to understand dark matter, one of the most enigmatic components of the universe. Observations and simulations suggest that bars interact with dark matter halos, exchanging angular momentum and potentially altering the shape and distribution of dark matter. These interactions provide a unique opportunity to test theories of dark matter and explore its role in galactic dynamics. For example, the presence of a bar can influence the rotation curve of a galaxy, providing clues about the distribution of dark matter within the halo. Beyond their physical and chemical effects, bars are a critical tool for understanding the early universe. Observations of high redshift galaxies reveal that bars were already present in some of the first galaxies to form after the Big Bang. These early bars are often less well-defined than their counterparts in nearby galaxies, reflecting the chaotic conditions of the early universe. Studying these structures provides valuable insights into the processes that shaped the first galaxies and set the stage for cosmic evolution. The emergence of new observational technologies is driving rapid progress in the study of galactic bars. The James Webb Space Telescope, JWST for example, is providing unprecedented views of distant galaxies, revealing the intricate structures of bars in the early universe. Meanwhile, large-scale surveys conducted by instruments like the Vera C. Rubin Observatory are enabling statistical studies of bars across a wide range of environments. These observations, combined with advances in computational modeling, are shedding light on the complex interplay of processes that govern the formation and evolution of bars. Despite these advances, many questions remain unanswered. For example, why do some galaxies develop bars while others do not? What determines the strength and longevity of a bar? How do bars interact with other galactic features, such as spiral arms, rings, and bulges? Addressing these questions will require a combination of observational, theoretical, and computational approaches, as well as a deeper understanding of the underlying physics. The study of galactic bars is not just about understanding these structures in isolation, it is about uncovering the fundamental processes that shape the universe. From their role in redistributing mass and angular momentum to their influence on star formation, chemical evolution, and dark matter, bars are a microcosm of the dynamic, interconnected systems that define the cosmos. Each discovery about bars brings us closer to answering the profound questions of how galaxies form, evolve, and interact with their environment. In the grand tapestry of the universe, galactic bars are a thread that weaves together diverse phenomena, providing a glimpse into the underlying order of the cosmos. As we continue to explore these structures, we are reminded of the complexity and beauty of the universe, and the endless possibilities for discovery that await us. The continued study of galactic bars pushes the boundaries of our understanding, serving as a reminder that even the most intricate cosmic structures are governed by the fundamental laws of physics. These central features of many galaxies, including our own Milky Way, encapsulate the dynamic processes at work in the universe and provide a lens through which we can observe its evolution. One area of growing interest is the role of stellar feedback in shaping the behavior of bars. Stellar feedback refers to the energy and momentum released into the interstellar medium by stars through processes such as supernovae, stellar winds, and radiation pressure. This feedback can have profound effects on the gas within a bar, influencing its density, temperature, and motion. For example, intense star formation within the bar region can generate feedback that disrupts the gas flow, temporarily halting the inward migration of material. Conversely, feedback may also compress gas, promoting further star formation in localized regions. Understanding this feedback loop is crucial for building accurate models of galaxy evolution. Galactic bars are also critical for exploring the interaction between baryonic matter and dark matter. While bars are primarily composed of stars, their formation and evolution are influenced by the surrounding dark matter halo. The transfer of angular momentum between the bar and the halo is a key mechanism driving the growth or weakening of bars. Interestingly, the shape and density profile of the dark matter halo can significantly affect the stability of the bar. Simulations show that a more concentrated halo may stabilize a bar, while a more diffuse halo could lead to its eventual dissolution. These interactions provide indirect evidence of the properties of dark matter, making bars an invaluable tool for testing competing theories of this mysterious component of the universe. In addition to their role in individual galaxies, bars influence the larger-scale structure of the universe. Galaxies are not isolated entities but are part of a cosmic web of filaments, voids, and clusters. Bars can affect how galaxies interact with their environment, particularly in dense regions such as galaxy clusters. For instance, the gravitational interactions between galaxies in a cluster can trigger or enhance bar formation, while the presence of a bar can alter the way a galaxy accretes material from the surrounding medium. By studying bars in different environments, astronomers can gain insights into the interplay between local and large-scale processes in shaping the universe. Another intriguing question is how bars contribute to the formation of supermassive black holes, SMBHs, at the centers of galaxies. As bars drive gas inward, they can deliver large amounts of material to the central region, providing the fuel needed for the growth of SMBHs. This process may explain why many barred galaxies host active galactic nuclei, AGN, regions of intense radiation powered by accretion onto a SMBH. However, the relationship between bars and AGN activity is complex and not fully understood. Observational studies have shown that not all barred galaxies have active nuclei, suggesting that other factors, such as the availability of gas and the history of galaxy interactions, also play a role. Recent advances in machine learning and artificial intelligence are revolutionizing the study of galactic bars. These tools are enabling astronomers to analyze vast datasets from surveys such as the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey (DS). By training algorithms to identify and classify bars and galaxy images, researchers can study their properties across different environments and redshifts. Machine learning is also being used to simulate the evolution of bars under various conditions, providing new insights into their dynamics and long-term behavior. Looking forward, the next generation of telescopes promises to transform our understanding of galactic bars. Instruments such as the Square Kilometre Array, SKA, and the Extremely Large Telescope, ELT, will provide unprecedented resolution and sensitivity, allowing astronomers to study bars in exquisite detail. These observations will shed light on the fine-scale structure of bars, including the distribution of stars, gas, and dust, as well as their interaction with other galactic components. The study of bars also raises profound questions about the origins of order and chaos in the universe. Bars are inherently chaotic structures, formed through the collective motion of countless stars. Yet, they exhibit remarkable regularity, maintaining their shape and structure over vast timescales. This duality reflects the balance between the deterministic laws of physics and the stochastic processes that govern the universe. By studying bars, we can gain a deeper appreciation of how order emerges from chaos on cosmic scales. Despite the progress made, many mysteries remain. For example, what triggers the initial instability that leads to bar formation? How do bars interact with spiral arms? And what determines the strength of this interaction? Why do some galaxies host long, well-defined bars while others have short or asymmetric ones? These questions highlight the complexity of galactic dynamics and the need for continued exploration. The study of galactic bars is not just about understanding these fascinating structures. It is about uncovering the fundamental principles that govern the universe, from the smallest scales of star formation to the largest scales of cosmic evolution. As we continue to unravel the mysteries of bars, we are reminded of the interconnectedness of all things. A single bar in a distant galaxy may hold the key to understanding the universe as a whole. The story of galactic bars is also a story of change, one that spans billions of years and encompasses countless transformations. The evolution of these structures mirrors the growth and development of the galaxies themselves, reflecting shifts in mass, energy, and dynamics over time. While current models provide a broad outline of their life cycle, the finer details of their growth, decline, and potential rebirth remain elusive. One of the most compelling mysteries is the lifespan of galactic bars. Observations suggest that bars may go through cycles of growth, weakening, and even dissolution over cosmic timescales. These cycles are influenced by several factors, including the redistribution of angular momentum, interactions with neighboring galaxies, and the consumption or exhaustion of gas in the central regions. However, it's unclear whether these cycles are universal or depend on specific properties of the host galaxy, such as its mass, morphology, or environment. Understanding these processes could unlock new insights into the broader patterns of galactic evolution. Another area of active research is the chemical enrichment of bars. As bars drive gas inward, they mix material from the outer regions of the galaxy with the inner regions, creating a unique chemical fingerprint. This mixing process can be observed through the distribution of elements such as oxygen, nitrogen, and iron, which are produced in the cores of stars and released into the interstellar medium through supernova explosions. By studying the chemical composition of bars, astronomers can trace the history of star formation and nucleosynthesis in these regions, offering a glimpse into the life cycle of matter itself. Bars also provide a natural laboratory for studying the dynamics of gas under extreme conditions. The intense gravitational forces within bars compress gas into dense filaments and clumps, where it may form stars or undergo further fragmentation. This gas dynamics is influenced by a delicate balance between gravity, pressure, and turbulence, creating a complex interplay that is challenging to model. Recent observations have revealed that some bars host regions of unusually high turbulence, which may inhibit star formation, while others contain highly ordered flows that funnel gas toward the center. These differences highlight the diversity of bar environments and the need for detailed studies to understand their behavior. The relationship between bars and galactic halos adds another layer of complexity. While bars are visible features of galaxies, they are embedded in massive halos of dark matter that extend far beyond their visible edges. These halos play a critical role in shaping the dynamics of bars, influencing their rotation speed, length, and strength. Conversely, bars can modify the density profile of the halo, redistributing dark matter and creating a more flattened or elongated structure. This interaction provides a unique opportunity to study the properties of dark matter, which remains one of the greatest unsolved mysteries in astrophysics. In recent years, astronomers have begun to explore the connection between bars and galaxy mergers. When galaxies collide or pass close to one another, their gravitational interactions can trigger the formation of a bar in one or both galaxies. These interactions also lead to the exchange of mass and angular momentum, potentially altering the properties of the bar or even causing it to disintegrate. Studying bars in merging galaxies can reveal how these dramatic events shape the structure and evolution of galaxies, as well as their ability to form new stars. The presence of bars in distant galaxies offers a glimpse into their role in the early universe. Observations from telescopes such as the Hubble Space Telescope and the James Webb Space Telescope have identified bars in galaxies that existed billions of years ago, during a period known as cosmic noon, when star formation was at its peak. These ancient bars may have played a crucial role in fueling the rapid growth of central black holes and triggering bursts of star formation. Comparing the properties of bars in the early universe to those in the present day can reveal how their role has changed over time, providing a broader context for understanding galactic evolution. One intriguing possibility is that some bars may be ephemeral structures, appearing and disappearing over relatively short timescales. Simulations suggest that bars can form and dissolve in response to changes in the distribution of mass and angular momentum within a galaxy. For example, a sudden influx of gas from a merger or accretion event could disrupt the stability of a bar, causing it to dissolve into a more spherical or elliptical structure. Alternatively, the bar may reform if conditions become favorable again, leading to a cycle of periodic growth and decay. This raises the question of whether bars are a universal feature of disk galaxies or a transient phase in their evolution. While most spiral galaxies observed today contain bars, a significant minority do not. It's unclear whether these galaxies have never formed bars, or if their bars have dissolved and not reformed. Understanding why some galaxies host bars while others do not could provide important clues about the initial conditions and evolutionary paths of galaxies. The study of galactic bars also intersects with the broader field of cosmology, particularly in the context of the large-scale structure of the universe. Bars influence how galaxies interact with their cosmic environment, including the filaments and voids of the cosmic web. For example, bars may affect the way galaxies accrete gas from their surroundings, altering their star formation rates and chemical evolution. They may also play a role in the alignment of galaxies within large-scale structures, contributing to patterns such as the cosmic spin alignment observed in some regions of the universe. As we look to the future, the continued study of galactic bars promises to uncover even more mysteries. The advent of next-generation telescopes and computational tools will enable astronomers to explore these structures in unprecedented detail, shedding light on their formation, evolution, and role in the cosmos. In doing so, we will not only deepen our understanding of bars but also gain new insights into the fundamental processes that govern the universe itself. The interplay between galactic bars and the broader mechanisms of the universe presents a rich tapestry of unresolved questions and tantalizing clues. One of the most fascinating avenues for future research lies in the relationship between galactic bars and dark matter. Dark matter, the enigmatic substance that makes up most of the universe's mass, remains elusive, but its gravitational influence is evident in the dynamics of galaxies. Bars provide a unique opportunity to probe dark matter halos because they are sensitive to the distribution of mass within their host galaxies. As bars rotate, they interact gravitationally with the surrounding dark matter, causing the dark matter to redistribute over time. This interaction can leave behind subtle signatures that astronomers can detect. For example, simulations show that bars may heat the dark matter halo, increasing its velocity dispersion and altering its density profile. These effects could help astronomers infer the properties of dark matter, such as its particle nature and its behavior on galactic scales. By comparing observations of barred galaxies to detailed simulations, researchers can test different theories of dark matter and refine their understanding of this mysterious component of the universe. Another frontier is the study of barred galaxies in different environments. Galaxies do not exist in isolation. They are part of larger structures such as groups, clusters, and superclusters. The environment of a galaxy can have a significant impact on its structure and evolution, including the formation and persistence of bars. For instance, galaxies in dense clusters experience frequent interactions with other galaxies and the hot intra-cluster medium, which can strip away gas and distort their shapes. These processes might suppress the formation of bars or lead to their early dissolution. On the other hand, interactions between galaxies can also trigger bar formation, as gravitational forces redistribute angular momentum and drive instabilities in the disk. By studying barred galaxies in diverse environments, astronomers can explore how external factors influence their evolution. Observations have shown that bars are less common in high-density environments, but the reasons for this trend are not fully understood. It may be related to the availability of gas, the frequency of interactions, or the influence of the cluster's tidal field. Understanding these relationships could provide new insights into the interplay between galaxies and their environments, as well as the factors that govern the prevalence of bars across the universe. The role of bars in galactic feedback mechanisms is another intriguing area of research. Feedback refers to the processes by which galaxies regulate their own growth, often through the interplay between stars, gas, and supermassive black holes. Bars play a key role in channeling gas toward the center of a galaxy, where it can fuel star formation and feed the central black hole. However, this inflow of gas can also trigger feedback processes that expel gas from the galaxy or heat it, preventing further star formation. One example of this is AGN, active galactic nucleus feedback, which occurs when a supermassive black hole accretes large amounts of matter and releases energy in the form of radiation, winds, or jets. Bars can drive the inflow of gas that powers AGN activity, but they can also be affected by the feedback itself. For instance, the intense radiation and outflows from an AGN can heat or expel the gas in the bar region, potentially disrupting the bar's structure or halting its ability to funnel gas inward. This dynamic interplay between bars and AGN feedback is a complex and poorly understood process that has significant implications for the evolution of galaxies. Advances in observational techniques are providing new opportunities to study these processes in detail. High-resolution imaging from telescopes like the Atacama Large Millimeter/Submillimeter Array (ALMA) and the James Webb Space Telescope (JWST) allows astronomers to map the distribution of gas, dust, and stars in barred galaxies with unprecedented precision. These observations reveal the intricate structures within bars, including dense gas filaments, star-forming regions, and turbulent flows. By combining these data with simulations, researchers can test models of bar dynamics and feedback, refining their understanding of the physical processes at play. The study of bars also intersects with the broader field of stellar population synthesis, which seeks to understand the properties of stars and their distribution within galaxies. Bars are often sites of intense star formation, but the stars they produce can have diverse properties depending on the conditions within the bar. For example, the strong gravitational forces in bars can lead to the formation of massive, short-lived stars that quickly explode as supernovae, enriching the surrounding gas with heavy elements. These processes can leave behind a distinct population of stars that serve as a fossil record of the bar's history. By analyzing the ages, compositions, and motions of stars in bars, astronomers can reconstruct their formation histories and trace their evolution over time. This approach, known as galactic archaeology, provides a powerful tool for studying the life cycles of bars and their impact on galaxies. It also offers a way to test theories of star formation under extreme conditions, as well as the effects of feedback and chemical enrichment on stellar populations. Looking further ahead, the study of galactic bars may benefit from the next generation of telescopes and space missions. Projects such as the Square Kilometre Array, SKA, and the European Extremely Large Telescope, ELT, promise to deliver unprecedented sensitivity and resolution, enabling astronomers to study bars in distant galaxies with the same level of detail currently possible for nearby systems. These observations will extend our understanding of bars across cosmic time, revealing how their properties have changed over billions of years and shedding light on their role in the broader context of cosmic evolution. As we continue to unravel the mysteries of galactic bars, we are reminded of the profound interconnectedness of the universe. Bars are not just features of individual galaxies. They are part of a vast cosmic web of interactions and processes that shape the structure and dynamics of the cosmos. By studying these enigmatic structures, we gain not only a deeper understanding of galaxies but also a glimpse into the fundamental forces that govern the universe itself. The future of research into galactic bars holds immense promise, especially as technology continues to push the boundaries of what we can observe and simulate. With the advent of machine learning and artificial intelligence, AI, astronomers are now capable of analyzing vast datasets that were previously too complex or time-consuming to study. AI can identify patterns, classify galaxy morphologies, and even predict the evolutionary pathways of barred galaxies based on observational data. These tools are revolutionizing the way we approach the study of galactic structures. One of the most exciting applications of AI in this field is the ability to simulate galactic evolution with extraordinary detail. Simulations such as those from the Illustris project or the Eagle project provide a virtual laboratory where researchers can test theories about bar formation and evolution. These simulations incorporate a wide range of physical processes, including gravity, hydrodynamics, star formation, and feedback, allowing scientists to explore how bars emerge and interact with other galactic components over billions of years. By comparing these simulations to real observations, astronomers can refine their models and gain deeper insights into the underlying physics. Another groundbreaking area of research is the study of barred galaxies in the early universe. Thanks to advanced telescopes like the James Webb Space Telescope, JWST, astronomers can now observe galaxies as they appeared billions of years ago, shortly after the Big Bang. Surprisingly, some of these early galaxies already show evidence of bar-like structures, challenging our understanding of how and when bars form. These observations suggest that bars may play a crucial role in the early stages of galaxy evolution, driving gas into the centers of young galaxies and fueling intense bursts of star formation. The discovery of early bars raises intriguing questions about the conditions needed for their formation. Did the early universe have unique properties that favored the rapid development of bars? Or are these structures simply the result of universal processes that operate across cosmic time? By studying early barred galaxies, researchers hope to uncover the answers to these questions and gain new insights into the role of bars in shaping the universe. In addition to their impact on star formation, bars may also influence the distribution of dark matter in the early universe. As bars interact with the dark matter halos of their host galaxies, they can leave behind imprints that provide clues about the nature of dark matter. For example, the way bars evolve in different environments could reveal whether dark matter is cold, made up of slow-moving particles, or warm, composed of faster-moving particles. These subtle effects are difficult to detect but could offer critical evidence for distinguishing between competing dark matter models. Another fascinating avenue of research is the role of bars in galactic mergers and interactions. When galaxies collide or interact, their structures can be profoundly altered. Bars are particularly sensitive to these interactions, as the gravitational forces involved can either trigger their formation or lead to their destruction. For example, a close encounter with another galaxy can destabilize the disk, causing a bar to form as angular momentum is redistributed. Alternatively, the intense gravitational forces in a merger can disrupt an existing bar, transforming it into a more chaotic structure. Studying these interactions provides a unique opportunity to understand how bars contribute to the larger-scale processes of galaxy assembly. Mergers and interactions are thought to play a major role in the formation of massive galaxies, and bars may act as intermediaries in this process, funneling gas and stars toward the center and triggering the growth of central bulges or supermassive black holes. Observations of interacting and merging galaxies often show bars in various stages of development, offering a dynamic view of how these structures evolve over time. The influence of bars extends beyond individual galaxies, shaping the broader structure of the universe itself. Bars are thought to contribute to the formation of large-scale structures such as cosmic filaments and walls, which are the building blocks of the cosmic web. By channeling gas and stars along specific pathways, bars may play a role in organizing the distribution of matter on these vast scales. This connection between small-scale structures like bars and the large-scale architecture of the universe highlights the interconnected nature of cosmic evolution. Moreover, the study of galactic bars has implications for our understanding of the chemical evolution of galaxies. Bars are efficient at transporting gas from the outer regions of a galaxy to its center, where it can be converted into new stars. This process not only fuels star formation but also enriches the central regions with heavy elements produced in previous generations of stars. Over time, this enrichment can lead to distinct chemical signatures in the stars and gas within the bar region. By analyzing the chemical composition of bars, astronomers can reconstruct their history and learn about the processes that shape them. For example, the relative abundance of elements like oxygen, carbon, and nitrogen can reveal how much gas has been funneled into the center and how efficiently it has been converted into stars. These chemical fingerprints provide a window into the life cycle of bars and their role in the broader context of galactic evolution. As we look to the future, the study of galactic bars promises to uncover new mysteries and deepen our understanding of the universe. With the continued development of cutting-edge technology, including next-generation telescopes, AI-driven analysis, and high-resolution simulations, astronomers are poised to make breakthroughs that were once unimaginable. Bars are more than just features of galaxies. They are key players in the cosmic drama, shaping the fate of stars, gas, and dark matter across the universe. The exploration of galactic bars is a testament to humanity's insatiable curiosity and our drive to understand the cosmos. Every discovery, no matter how small, brings us closer to unraveling the mysteries of the universe and our place within it. The story of bars is far from over, and as we continue to push the boundaries of knowledge, we can only imagine what new revelations await. The journey to understanding galactic bars is one of the most captivating sagas in astronomy. While we've uncovered many details about their formation, evolution, and role in shaping galaxies, it feels as though we're only scratching the surface. Bars, despite being such prominent structures, are filled with subtle complexities that challenge our understanding of how galaxies work on every scale, both in isolation and as part of the cosmic web. One of the biggest unanswered questions revolves around how environmental factors influence the formation and survival of galactic bars. For instance, galaxies exist in diverse settings, from isolated regions of the universe to dense galaxy clusters. The gravitational interactions within these environments can have profound effects on a galaxy's morphology. In clusters, for example, galaxies experience ram pressure stripping, where the gas within them is stripped away due to the high-speed motion through the hot intra-cluster medium. This can limit the amount of gas available for bar formation or star formation within the bar itself. On the other hand, interactions in galaxy pairs or small groups can induce bars through tidal forces, creating some of the most dramatic evolutionary pathways for these galaxies. There is also the intriguing question of how long bars persist. Do they remain stable over the lifetime of a galaxy, or do they dissolve and reform multiple times? Current simulations suggest that bars can be long-lived but are not entirely permanent structures. Over time, a bar can weaken due to angular momentum exchanges with other components of the galaxy, such as the halo or disk. Additionally, the inflow of gas, or lack thereof, can either sustain a bar by replenishing its material or starve it, leading to its gradual dissolution. Understanding this life cycle requires both detailed observations of galaxies at different stages of their evolution and simulations that incorporate realistic physics. Astronomers are also exploring how bars interact with supermassive black holes, SMBHs, at the centers of galaxies. Bars are efficient at driving gas into the galactic core, where it can fuel the growth of SMBHs. This raises fascinating questions about the role of bars in triggering active galactic nuclei, AGN, and the subsequent feedback processes that can regulate galaxy evolution. AGN feedback, such as powerful winds or jets emitted by the black hole, can impact star formation by either compressing gas into new stars or blowing it away entirely. The interplay between bars and black holes is a dynamic and complex relationship that likely varies across different types of galaxies and cosmic epochs. Another layer of complexity lies in understanding the role of bars in galaxies that are undergoing major changes, such as transitioning from being gas-rich spiral galaxies to gas-pearl lenticular or elliptical galaxies. These transitions are often driven by external factors like mergers or internal processes like the depletion of star-forming material. Bars could act as transitional structures, redistributing material and reshaping the dynamics of a galaxy during these evolutionary phases. Observing galaxies in the midst of these transitions can provide valuable insights into the role of bars as agents of change. To gain a truly comprehensive understanding of galactic bars, astronomers are also turning their attention to the unseen, dark matter. Bars interact with the dark matter halos that surround galaxies, and these interactions can leave measurable imprints. For instance, the presence of a bar can modify the density profile of the dark matter halo, leading to a phenomenon known as a cusp core transformation. This occurs when the bar redistributes dark matter from the central regions to the outskirts of the halo, creating a flatter density profile. Studying these effects not only enhances our understanding of bars but also provides indirect evidence for the nature of dark matter itself. One of the most exciting aspects of studying bars is the potential to use them as cosmic time machines. Since light takes time to travel across vast distances, observing galaxies at different distances allows us to look back in time and see how bars formed and evolved over billions of years. By comparing nearby galaxies with those at great distances, astronomers can piece together a timeline of bar formation and evolution. This approach has already yielded surprising discoveries, such as the presence of bars in some of the earliest galaxies observed, challenging the idea that bars are exclusively features of mature galaxies. Moreover, bars could hold clues about the ultimate fate of galaxies. In some models of cosmic evolution, galaxies are thought to undergo a secular process, where internal mechanisms, including bars, drive their evolution over time. Bars might play a pivotal role in this process by redistributing mass and angular momentum, effectively setting the stage for the galaxy's long-term development. Whether this leads to the formation of massive bulges, the cessation of star formation, or the eventual fading into a more passive state is still an open question. As we continue to study bars, the importance of multi-wavelength astronomy cannot be overstated. Observing galaxies across different parts of the electromagnetic spectrum reveals complementary information. For example, infrared observations are particularly useful for studying bars because they penetrate the dust that often obscures the central regions of galaxies in visible light. Infrared data from telescopes like the Spitzer Space Telescope and the JWST provide detailed views of the stars and gas within bars, helping astronomers understand their structure and composition. Radio astronomy adds yet another layer of understanding by revealing the distribution and motion of cold gas in galaxies. This gas is the raw material for star formation, and its interaction with the bar can determine how efficiently new stars are created. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, are uncovering the intricate details of gas flows within bars, providing critical data for understanding their role in galactic evolution. The study of bars is also benefiting from advances in spectroscopy, which allows astronomers to measure the motions of stars and gas within galaxies. By analyzing the redshifts and blue shifts of light emitted from different regions of a galaxy, researchers can construct detailed maps of its internal dynamics. These maps are essential for understanding how bars rotate, interact with other components, and evolve over time. Looking to the future, next-generation telescopes such as the European Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, promise to revolutionize our understanding of bars. These telescopes will provide unprecedented resolution and sensitivity, enabling astronomers to study bars in distant galaxies with the same level of detail currently possible only for nearby systems. Combined with advances in computational power and simulation techniques, these tools will unlock new opportunities to explore the mysteries of galactic bars. Ultimately, the study of galactic bars is a testament to the interconnected nature of the universe. These seemingly simple structures are intricately linked to processes on all scales, from the formation of individual stars to the evolution of entire galaxies and the large-scale structure of the cosmos. As we continue to unravel their secrets, we gain not only a deeper understanding of bars but also a greater appreciation for the complexity and beauty of the universe as a whole. The interplay of galactic bars with the broader cosmic ecosystem reveals layers of complexity that highlight their significance in the grand narrative of the universe. Bars are far more than just striking visual features. They are dynamic, evolving entities that play pivotal roles in the life cycle of galaxies, shaping everything from their structure to their star-forming potential. The closer we examine these structures, the more we realize how integral they are to understanding the fundamental mechanics of the cosmos. One of the most captivating aspects of galactic bars is their ability to function as conduits for matter within galaxies. The gravitational forces exerted by the bar create torque, which drives gas inward toward the galaxy's center. This process has profound implications for the central regions of galaxies, where the accumulation of gas can lead to bursts of star formation or the feeding of a central supermassive black hole. These phenomena not only influence the galaxy's core but can also send ripples throughout the galaxy, altering its evolution in significant ways. For instance, when a bar funnels gas toward the central regions, it can trigger the formation of a dense nuclear star cluster. These clusters, found in many galaxies, are among the densest star systems in the universe. They act as cosmic laboratories, offering insights into how stars form and interact in extreme environments. Additionally, the inflow of gas can feed the supermassive black hole at the galaxy's core, potentially igniting an active galactic nucleus, AGN. These AGNs can release immense amounts of energy, driving powerful winds that can regulate star formation by either compressing or expelling gas. The relationship between bars and star formation is one of the most actively studied topics in galactic astronomy. Bars can act as both enablers and suppressors of star formation, depending on their specific characteristics and the environment of the galaxy. In some cases, bars create regions of intense star formation along their length, known as star-forming ridges. These ridges are often rich in molecular gas, the primary ingredient for star formation. Observations of nearby barred galaxies, such as the iconic NGC 1300, reveal spectacular chains of young, bright stars tracing the length of their bars. Conversely, bars can also suppress star formation by depleting the gas in the outer regions of a galaxy. As the bar channels gas inward, it can leave the outer disk with insufficient material to sustain star formation. This creates a contrast between the vibrant central regions and the quieter outskirts, a pattern observed in many barred galaxies. Understanding this dual role of bars in promoting and suppressing star formation is crucial for constructing a comprehensive picture of galactic evolution. The role of bars extends beyond individual galaxies to their interactions with the larger cosmic environment. Galaxies are not isolated entities. They exist within the cosmic web, surrounded by neighbors and embedded in dark matter halos. Bars can amplify the effects of these external influences, making galaxies more susceptible to interactions with their environment. For example, in galaxy clusters, bars can enhance the effects of tidal forces, leading to more pronounced structural changes. In isolated galaxies, bars can act as catalysts for internal transformations, driving the transition from one galactic morphology to another. The longevity of bars is another area of active research. While some bars appear to be long-lived features, others seem to dissolve over time, only to reform later. This cyclical behavior raises intriguing questions about the factors that influence the stability of bars. One key factor is the distribution of angular momentum within the galaxy. Bars can exchange angular momentum with the disk, halo, and even neighboring galaxies, leading to changes in their structure and strength. Advanced simulations suggest that bars are more likely to persist in galaxies with massive, centrally concentrated bulges, which can stabilize the bar against external perturbations. Dark matter, the enigmatic substance that dominates the mass of the universe, also plays a crucial role in the life cycle of bars. While dark matter is invisible, its gravitational effects are measurable, and bars interact with the dark matter halo surrounding a galaxy. These interactions can lead to the redistribution of dark matter, creating observable changes in the galaxy's rotation curve. Studying these effects provides indirect evidence for the nature of dark matter, making bars valuable tools for probing this fundamental mystery of modern physics. Observations across the electromagnetic spectrum have revolutionized our understanding of bars. Infrared telescopes, such as the Spitzer Space Telescope, have been particularly instrumental in studying bars, as they can penetrate the dust that obscures the central regions of galaxies in visible light. Infrared data reveal the stellar mass distribution within bars, providing critical insights into their structure and dynamics. Radio telescopes, on the other hand, map the distribution of cold gas, allowing astronomers to study how bars influence the flow of material within galaxies. Spectroscopy, the study of light's interaction with matter, has also been invaluable. By analyzing the spectra of light emitted by stars and gas within bars, astronomers can determine their chemical composition, temperature, and motion. These data are essential for understanding the physical processes occurring within bars, from star formation to gas dynamics. For instance, spectroscopic studies have revealed that the gas channeled by bars often exhibits signs of shock heating, a consequence of the intense gravitational forces at play. The future of bar research is incredibly promising, thanks to next-generation observatories and advances in computational modeling. Telescopes like the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory are poised to provide unprecedented views of bars in both nearby and distant galaxies. These instruments will allow astronomers to study the faintest and most distant bars, providing a more complete picture of their role in galactic evolution. Simulations, too, are becoming increasingly sophisticated, incorporating the effects of dark matter, star formation, and feedback processes. These models are essential for testing hypotheses about the formation and evolution of bars, as well as their interactions with other galactic components. By comparing simulations with observations, astronomers can refine their understanding of the physical processes driving the behavior of bars. As we continue to explore the mysteries of galactic bars, one thing is clear: these structures are far more than mere aesthetic features. They are dynamic engines of change, shaping the destiny of galaxies and providing invaluable insights into the workings of the universe. Each discovery brings us closer to unraveling the complexities of these cosmic phenomena, opening new windows into the intricate dance of matter and energy that defines our universe. The study of galactic bars also illuminates their connection to the earliest stages of galaxy formation. When we observe the universe's most distant galaxies, we are effectively looking back in time, witnessing how galaxies appeared billions of years ago. Surprisingly, some of these ancient galaxies already exhibit well-formed bars. This challenges our understanding of galaxy formation and evolution, as bars were traditionally thought to emerge in more mature systems after the initial chaotic phases of galactic assembly. The discovery of bars in young galaxies suggests that their formation might occur much earlier than previously assumed, potentially influenced by the dynamic interplay of gas, dark matter, and gravitational forces. Simulations and observations indicate that instabilities in the galactic disk can lead to the rapid development of a bar, especially in galaxies with high gas content. These findings hint at the possibility that bars may have played a significant role in shaping galaxies from the very beginning, influencing star formation and the distribution of matter even in the universe's infancy. Furthermore, bars provide critical clues about the mysterious processes governing the redistribution of angular momentum. This is a fundamental aspect of galactic dynamics, as it dictates how material moves within a galaxy and how its structure evolves over time. Bars act as powerful engines for angular momentum transfer, redistributing energy between the galaxy's disk, bulge, and halo. This process can lead to the growth of the central bulge, the thinning of the disk, and even the eventual dissolution of the bar itself. In addition to their role in internal dynamics, bars are also key players in galaxy mergers and interactions. When two galaxies collide or pass close to one another, their gravitational interactions can trigger the formation of a bar or amplify an existing one. In such scenarios, the bar acts as a mediator, funneling gas toward the center and igniting intense episodes of star formation. These starburst events can temporarily transform the galaxy's appearance and structure, leaving behind remnants of the interaction that can be observed billions of years later. Moreover, bars are not static structures; they evolve over time, influenced by both internal and external factors. Observational data and simulations reveal that bars can grow longer and stronger as they age, a process driven by the gradual accumulation of mass along their length. However, bars can also weaken and dissolve, particularly in galaxies where external forces disrupt their stability. This dynamic nature makes bars fascinating subjects of study, as their evolution provides insights into the life cycles of galaxies and their interactions with the cosmic environment. One of the most intriguing aspects of bar evolution is the potential for bar rejuvenation. In some galaxies, bars that have weakened or dissolved can reform under the right conditions, such as a renewed inflow of gas or changes in the galaxy's gravitational potential. This cyclical behavior underscores the resilience of bars and their ability to adapt to changing circumstances within their host galaxies. The influence of bars extends beyond the visible matter in galaxies, offering a unique window into the elusive realm of dark matter. Because bars interact with the dark matter halo, they can create observable effects that provide indirect evidence for the properties of dark matter. For instance, the distribution and motion of stars and gas within a bar are shaped by the gravitational pull of both the visible and dark matter components. By studying these patterns, astronomers can infer the characteristics of the dark matter halo, such as its density and shape. These investigations have profound implications for our understanding of dark matter, one of the greatest mysteries in modern physics. Bars serve as natural laboratories for testing theories about dark matter, from its distribution within galaxies to its role in the larger cosmic web. The study of bars, therefore, bridges the gap between galactic dynamics and cosmology, contributing to our broader quest to decipher the nature of the universe. The advent of cutting-edge observational technology has revolutionized our ability to study bars in unprecedented detail. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have enabled astronomers to map the cold molecular gas within bars with incredible precision. These observations reveal the intricate structure of gas flows, from the large-scale inflow along the bar to the small-scale turbulence within star-forming regions. ALMA's data have also uncovered surprising features, such as streamers of gas that extend beyond the bar, connecting the central regions to the outer disk. Similarly, advancements in space-based telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, have provided high-resolution images of bars in distant galaxies. These observations offer a glimpse into the early stages of bar formation and their evolution over cosmic time. By comparing these snapshots to nearby galaxies, astronomers can trace the life cycle of bars and identify the factors that influence their longevity and structure. The role of computational modeling in understanding bars cannot be overstated. Simulations have become indispensable tools for exploring the complex dynamics of barred galaxies. By recreating the conditions within galaxies, these models allow researchers to test hypotheses about bar formation, evolution, and interaction with other galactic components. For example, simulations have demonstrated how the distribution of dark matter affects the stability of bars, providing key insights into the interplay between visible and invisible matter. In addition to their scientific significance, bars are a source of wonder and inspiration, captivating astronomers and the public alike. Their striking appearance, with bright, elongated structures cutting through the heart of galaxies, evokes a sense of cosmic artistry. Each bar tells a story of dynamic processes and interactions, a testament to the intricate and ever-changing nature of the universe. As we continue to unravel the mysteries of galactic bars, one thing is clear: they are not mere features of galaxies but vital components that shape their evolution and reveal the underlying forces at play in the cosmos. Each discovery adds another piece to the puzzle, bringing us closer to a comprehensive understanding of these fascinating structures and their role in the grand tapestry of the universe. The intricate dynamics of galactic bars extend beyond their internal mechanisms, touching on their role in the larger galactic ecosystem. One of the most compelling aspects of these structures is their ability to influence the fate of surrounding dwarf galaxies and satellite systems. When a barred galaxy interacts with a smaller companion, the gravitational pull of the bar can strip material from the satellite galaxy, redistributing it across the primary galaxy's disk or funneling it inward to fuel star formation. This process, known as tidal stripping, not only impacts the smaller galaxy but also contributes to the growth and enrichment of the larger system. Interestingly, bars may also help regulate the flow of cosmic gas into galaxies. The cosmic web, the large-scale structure of the universe, channels gas into galaxies through filaments, providing the raw material for star formation. Bars act as gatekeepers in this process, directing the incoming gas toward the central regions where it can be converted into stars or feed the central black hole. This controlled inflow prevents the gas from being dispersed throughout the galaxy, ensuring that it is used efficiently to sustain the galaxy's evolution. The interplay between bars and supermassive black holes is another area of active research. Nearly every massive galaxy hosts a supermassive black hole at its center, and the activity of these black holes, whether quiescent or active, can profoundly influence the host galaxy. Bars are particularly effective at transporting gas to the central regions of galaxies, where it can accumulate in the vicinity of the black hole. This inflow of material can trigger active galactic nuclei, AGN, phases, during which the black hole accretes matter at high rates, releasing tremendous energy in the form of radiation and outflows. The feedback from AGN activity can have dramatic consequences for the host galaxy, including the suppression of star formation by heating or expelling gas. Bars, therefore, are not merely passive structures but active participants in shaping the central environments of galaxies. Their ability to fuel AGN activity highlights their role in the coevolution of galaxies and their central black holes, a relationship that lies at the heart of modern astrophysics. Another intriguing aspect of galactic bars is their potential connection to galactic spin. Observations suggest that the angular momentum of a galaxy, its rotational speed and direction, may influence the formation and orientation of bars. For instance, galaxies with higher rotational speeds are more likely to develop long and prominent bars, while those with slower spins may host shorter or weaker bars. This relationship underscores the importance of angular momentum in determining a galaxy's structural properties and its evolutionary trajectory. Moreover, the orientation of a bar relative to the rest of the galaxy can provide clues about the past interactions and mergers that shaped it. For example, a bar that is misaligned with the galaxy's disk may indicate a history of gravitational disturbances, such as a collision with another galaxy. These misalignments are valuable markers of a galaxy's dynamical history, offering a glimpse into the turbulent processes that govern galaxy formation and evolution. The study of bars also raises questions about the universality of galactic structures. While bars are common in disk galaxies, not all galaxies possess them. This variation suggests that the formation of bars depends on specific initial conditions, such as the mass distribution, gas content, and the presence of a central bulge. Understanding why some galaxies develop bars while others do not is a key challenge in astrophysics, as it touches on the broader question of what determines the diversity of galactic morphologies. One potential answer lies in the role of dark matter halos. The distribution and density of dark matter around a galaxy can influence its susceptibility to bar formation. Simulations reveal that galaxies with concentrated dark matter halos are less likely to develop bars, as the halo's gravitational pull stabilizes the disk against the instabilities that lead to bar formation. This insight highlights the intricate connection between visible and dark matter, emphasizing the need to study both components to fully understand galactic dynamics. In addition to their scientific significance, bars serve as natural laboratories for studying the interplay of physics and astronomy. Their complex dynamics encompass a wide range of physical processes, from fluid dynamics and gas flows to gravitational interactions and angular momentum transfer. By studying bars, researchers gain a deeper appreciation for the interconnectedness of these phenomena, advancing our understanding of both individual galaxies and the broader cosmic framework. Observationally, galactic bars provide an opportunity to test theoretical models and predictions. The distribution of stars and gas within a bar, the strength and speed of its rotation, and its interaction with other galactic components are all measurable quantities that can be compared to simulations. These comparisons validate or refine our models, ensuring that they accurately reflect the underlying physics. In this way, the study of bars serves as a bridge between theory and observation, uniting the two pillars of modern astronomy. As our observational capabilities continue to improve, the future of bar research looks increasingly promising. Upcoming telescopes, such as the Vera C. Rubin Observatory, are expected to revolutionize our understanding of galactic bars by providing high-resolution data on millions of galaxies. This wealth of information will enable astronomers to conduct large-scale statistical studies, identifying trends and correlations that were previously inaccessible. These surveys will shed light on the frequency of bars, their evolution over cosmic time, and their impact on the broader galactic ecosystem. The study of galactic bars is not merely an academic pursuit but a quest to unravel the fundamental processes that govern the universe. These structures, with their striking appearance and dynamic behavior, hold the keys to understanding the complex interplay of matter, energy, and gravity on cosmic scales. Each discovery adds a new chapter to the story of galaxies, bringing us closer to answering the timeless question of how the universe works. The complexity of galactic bars extends into their influence on interstellar environments, particularly the creation of regions conducive to starburst activity. In barred galaxies, the concentrated flow of gas toward the central regions not only triggers ordinary star formation but also results in bursts of intense, rapid star formation. These starburst regions, often located near the ends of the bar or in the central nucleus, serve as hotspots of stellar birth. The interplay of gravitational forces, turbulence, and gas compression in these zones creates an ideal environment for the collapse of molecular clouds, leading to the formation of massive, short-lived stars that dominate their surroundings with their intense radiation. The stars born in these regions often play a pivotal role in shaping their host galaxies. Their radiation and stellar winds disperse the surrounding gas, halting further star formation in their immediate vicinity, while enriching the interstellar medium with heavy elements. These elements, created during the nuclear fusion processes within stars, are the building blocks of planets, moons, and potentially life itself. Galactic bars, therefore, indirectly contribute to the cosmic chemical enrichment that underpins the evolution of complexity in the universe. Bars also play a role in shaping galactic disks over time. The redistribution of gas, dust, and stars caused by the bar's gravitational influence alters the density and composition of the disk. This process can lead to the formation of spiral arms, which are often more pronounced in galaxies with strong bars. Spiral arms, in turn, act as wave patterns that compress gas and dust as they rotate, fostering additional star formation. In this sense, bars and spirals work in tandem, creating a feedback loop that drives the dynamic evolution of galaxies. Beyond individual galaxies, bars contribute to the broader cosmic web by influencing the large-scale distribution of matter. For instance, the gravitational forces exerted by bars can amplify density waves in the surrounding galactic environment, enhancing the formation of tidal streams and bridges between galaxies. These features, often visible in interacting systems, provide a glimpse into the dynamic interplay between galaxies and their surroundings. Bars thus serve as connectors in the cosmic network, linking the evolution of individual galaxies to the larger structure of the universe. The orientation and shape of bars also provide valuable insights into the past interactions of galaxies. For example, a bar that appears elongated or twisted may indicate a history of gravitational disturbances caused by close encounters or mergers. By studying these features, astronomers can reconstruct the evolutionary history of galaxies, identifying the events that shaped their current forms. This forensic approach to astronomy highlights the importance of bars as markers of galactic memory, preserving the imprint of past interactions in their structure. Interestingly, the study of bars has also revealed patterns of resonance phenomena within galaxies. Resonances occur when the rotational speed of the bar matches the orbital speed of stars and gas in specific regions of the galaxy. These resonances create zones of enhanced gravitational influence, where material tends to accumulate. For instance, the corotation resonance, where the bar and the disk rotate at the same angular velocity, often marks a boundary between the inner and outer regions of the galaxy. Understanding these resonances provides crucial insights into the internal dynamics of galaxies and the mechanisms that sustain their structure over time. The role of bars in galaxy evolution extends to their interaction with dark matter halos. While dark matter is invisible and interacts primarily through gravity, its distribution and density profoundly influence the stability and behavior of bars. For example, a dense dark matter halo can stabilize the outer regions of a galaxy, preventing the bar from extending too far or rotating too quickly. Conversely, a less concentrated halo allows the bar to grow and evolve more freely. These interactions underscore the importance of dark matter in shaping the observable universe, linking the study of bars to one of the most profound mysteries in modern astrophysics. Moreover, bars are not static features. They evolve over time, often undergoing significant changes in size, shape, and strength. This evolution is driven by various factors, including the exchange of angular momentum between the bar and the surrounding disk, the accretion of material from the cosmic web, and interactions with neighboring galaxies. By studying the evolution of bars, astronomers gain a dynamic perspective on the life cycles of galaxies, from their formation to their eventual transformation into elliptical or lenticular systems. The persistence of bars in galaxies also raises intriguing questions about the longevity of these structures. While some bars appear stable over billions of years, others seem to dissolve or weaken within shorter time frames. This variability suggests that bars are influenced by a delicate balance of forces, including the gravitational potential of the galaxy, the distribution of gas and stars, and external disturbances. Unraveling the factors that determine the lifespan of bars remains a central challenge in the study of galaxy evolution. Theoretical simulations have been instrumental in advancing our understanding of galactic bars. By creating realistic models of galaxies, researchers can test various scenarios for bar formation and evolution, exploring how changes in initial conditions or external influences affect their development. These simulations have revealed surprising phenomena, such as the spontaneous formation of bars and galaxies that initially lacked them, driven by subtle instabilities in the disk. These findings highlight the dynamic and emergent nature of bar formation, challenging traditional views of galaxies as static, unchanging systems. At the same time, observations of bars in the early universe are shedding light on their role in cosmic history. The discovery of barred galaxies at high redshifts, when the universe was only a few billion years old, suggests that bars have been a fundamental feature of galaxy formation from the very beginning. These early bars likely played a crucial role in the rapid growth of galaxies during the cosmic dawn, channeling material to the central regions to fuel intense episodes of star formation and black hole activity. In essence, galactic bars are not merely structural features but dynamic engines of cosmic evolution. Their influence extends across multiple scales, from the internal dynamics of galaxies to their interactions with the larger universe. By studying bars, we gain a deeper appreciation for the intricate web of processes that govern the cosmos, revealing the hidden order behind the apparent chaos of the universe. The study of galactic bars provides a profound window into the interplay between order and chaos in the universe. These structures represent a dynamic equilibrium, a tug-of-war between the gravitational forces of stars, gas, and dark matter, and the chaotic instabilities that seek to disrupt them. Understanding this balance is key to unraveling the mysteries of galaxy formation and evolution, as well as the larger-scale forces that shape the universe. One particularly fascinating aspect of bars is their role in redistributing angular momentum within galaxies. Angular momentum, the rotational inertia of a system, governs the motion of stars, gas, and other components within a galaxy. Bars act as conduits for angular momentum transfer, redistributing it between the disk, bulge, and dark matter halo. This process profoundly affects the structure and behavior of the galaxy over time. For instance, when a bar forms, it tends to slow down as it loses angular momentum to the surrounding disk or halo. This deceleration can cause the bar to grow longer and more elongated, altering its gravitational influence. Meanwhile, the angular momentum transferred to the disk can trigger the formation of spiral arms or warp the outer regions of the galaxy. These feedback effects illustrate how bars act as catalysts for change, driving the evolution of galaxies in unexpected ways. Another critical aspect of bar dynamics is their interaction with central supermassive black holes. Nearly every massive galaxy harbors a supermassive black hole at its core, and bars play a pivotal role in regulating the flow of material into these enigmatic objects. By funneling gas toward the galactic nucleus, bars provide the fuel needed for black hole growth and activity. This process, known as accretion, releases enormous amounts of energy, often in the form of high-energy radiation or powerful jets. The energy output from active galactic nuclei, AGN, can have far-reaching consequences for the host galaxy. For example, intense radiation from an AGN can heat the surrounding gas, preventing it from cooling and forming new stars. This feedback mechanism, known as quasar-mode feedback, is thought to play a key role in regulating star formation in massive galaxies, leading to their eventual transformation into red and dead elliptical systems. On the other hand, the interaction between bars and black holes is not one-sided. The gravitational influence of a central black hole can affect the stability and longevity of a bar. For example, a particularly massive black hole may disrupt the orbits of stars within the bar, weakening or even dissolving it over time. This complex interplay between bars and black holes highlights the interconnected nature of galactic evolution, where seemingly unrelated processes are intricately linked. In addition to their influence on internal galactic dynamics, bars also play a role in shaping the larger cosmic environment. For example, bars can enhance the formation of tidal streams, long, thin structures of stars and gas that extend beyond the main body of a galaxy. These streams often form during interactions with neighboring galaxies, providing clues about the history of these encounters. Bars amplify these effects by funneling material outward, creating more pronounced streams that are easier to observe. Similarly, Bars can influence the distribution of satellite galaxies and other companions. By disturbing the gravitational potential of the host galaxy, bars can alter the orbits of nearby objects, pulling them closer or pushing them farther away. These interactions may explain some of the peculiar arrangements of satellites observed around certain galaxies, such as the Milky Way. The role of bars in the Milky Way itself has been a subject of intense study. The Milky Way's central bar, spanning approximately 27,000 light-years, is a defining feature of our galaxy. Observations suggest that the bar is relatively young, having formed within the last few billion years. Its presence has significant implications for the structure and behavior of the galaxy, influencing the orbits of stars, the distribution of gas, and the formation of spiral arms. One intriguing aspect of the Milky Way's bar is its potential role in shaping the solar neighborhood. Some studies suggest that the bar's gravitational influence may have perturbed the orbits of stars in the disk, creating patterns in their velocities. These patterns, known as moving groups, provide valuable insights into the dynamics of the galaxy and its past interactions. Understanding these effects could help astronomers reconstruct the history of the Milky Way and its interactions with nearby galaxies, such as the Andromeda Galaxy. The discovery of bars in the early universe also raises fascinating questions about their origin and evolution. How did these structures form in the chaotic environment of the young cosmos, where galaxies were still in the process of assembling? One possibility is that bars emerged from instabilities in the primordial disks of gas and stars, triggered by the rapid accretion of material from the cosmic web. Alternatively, bars may have formed through interactions with neighboring galaxies, which were more frequent in the early universe. Observations of high-redshift barred galaxies suggest that these structures played a crucial role in shaping the early universe. By channeling gas into the central regions, bars may have accelerated the formation of massive black holes and the growth of galactic bulges. These processes, in turn, influenced the large-scale distribution of matter and the formation of galaxy clusters. Studying these early bars provides a unique opportunity to explore the fundamental processes that shape the universe as we see it today. As our understanding of galactic bars deepens, new questions continue to emerge. For example, why do some galaxies form strong, prominent bars while others remain barless? What role do environmental factors, such as interactions with neighboring galaxies or the influence of dark matter, play in determining the properties of bars? And how do bars interact with other structures, such as rings, lenses, and spiral arms, to create the diverse array of galaxy shapes observed in the universe? Answering these questions requires a multifaceted approach, combining observations across the electromagnetic spectrum with advanced theoretical models and simulations. Observations from cutting-edge telescopes, such as the James Webb Space Telescope and the Vera C. Rubin Observatory, are expected to revolutionize our understanding of bars by providing unprecedented views of their structure and dynamics. Meanwhile, advances in computational power enable the creation of more realistic simulations, capturing the complex interplay of forces that govern the evolution of bars. The study of galactic bars is not just about understanding a single feature of galaxies. It is a journey into the heart of cosmic evolution. Bars are the engines that drive the redistribution of matter and energy within galaxies, shaping their structure, behavior, and fate. They are key players in the cosmic dance of creation and destruction, where stars are born, galaxies collide, and the universe evolves. The deeper we delve into the mysteries of galactic bars, the more evident it becomes that they are pivotal to understanding the life cycles of galaxies. Bars serve as dynamic hubs, orchestrating the movement of gas, stars, and dark matter, and their influence extends far beyond their visually striking appearance. To appreciate their significance fully, we must examine their intricate interactions, origins, and implications for the broader universe. One of the most fascinating aspects of galactic bars is their potential to reveal the distribution of dark matter within galaxies. Dark matter, the enigmatic substance that constitutes a significant portion of the universe's mass, does not emit, absorb, or reflect light, making it invisible to direct observation. However, its presence can be inferred through its gravitational effects. Bars, as massive and dynamic structures, interact with dark matter halos surrounding galaxies, providing indirect evidence of their properties. When a bar forms, it interacts gravitationally with the surrounding dark matter halo, creating patterns and resonances that astronomers can study. These interactions can cause the bar to lose angular momentum, which is then absorbed by the dark matter halo. This exchange affects the rotation speed and shape of the bar, offering valuable clues about the density and distribution of dark matter. By comparing observations of bars with theoretical models, scientists can refine their understanding of dark matter's role in galaxy formation and evolution. Furthermore, bars offer insights into the mysterious phenomenon of galactic migration. Over time, stars within a galaxy can move from one region to another, altering their radial position in the galactic disk. This process, known as radial migration, is often driven by gravitational interactions with spiral arms or bars. Bars, in particular, are highly effective at inducing radial migration because of their strong gravitational influence and resonant patterns. As stars migrate, they can carry with them information about their original environment, such as their chemical composition and age. This makes radial migration a valuable tool for reconstructing the history of a galaxy. By studying the distribution of stars and their properties in barred galaxies, astronomers can trace the movement of stellar populations and gain insights into the galaxy's past interactions and evolution. Bars also play a critical role in the redistribution of chemical elements within galaxies. When gas flows toward the galactic center due to the gravitational pull of a bar, it triggers intense star formation in the central regions. The resulting supernovae release heavy elements, such as iron and oxygen, into the surrounding environment. These elements are then mixed with the inflowing gas, enriching the central regions with metals and altering the chemical composition of the galaxy. This process, known as chemical enrichment, has far-reaching implications for the evolution of galaxies and the formation of new stars and planets. By studying the metallicity gradients in barred galaxies, how the concentration of heavy elements changes with distance from the center, scientists can gain insights into the efficiency and timescales of this enrichment process. This, in turn, helps us understand the conditions that gave rise to our own solar system and the broader chemical evolution of the universe. Another intriguing question is how bars influence the overall morphology of galaxies. The presence of a bar can dramatically alter a galaxy's appearance, transforming a simple disk into a more complex structure with rings, lenses, and other features. These morphological changes are not merely cosmetic. They reflect the underlying dynamics and evolutionary history of the galaxy. For example, rings often form as a result of resonances between the bar and the orbits of stars and gas in the disk. These resonances create regions where material accumulates, forming bright, circular features. Rings can provide valuable information about the pattern speed of the bar, the rate at which it rotates, and the distribution of matter within the galaxy. By studying these features, astronomers can uncover the secrets of a galaxy's internal dynamics and its interaction with the surrounding environment. The study of galactic bars also has implications for understanding galaxy mergers and interactions. When two galaxies collide, their gravitational forces can trigger the formation of a bar in one or both galaxies. These bars can then influence the subsequent evolution of the merger, redistributing material and shaping the final structure of the resulting galaxy. In some cases, bars may even survive the merger process, providing a lasting imprint of the galaxy's tumultuous past. Moreover, the presence of a bar can affect the formation of satellite galaxies and tidal dwarf galaxies, small systems that form from the debris of galaxy collisions. By funneling material outward, bars can contribute to the formation of these satellite systems, enriching our understanding of galaxy formation on smaller scales. Studying these interactions offers a glimpse into the hierarchical nature of galaxy formation, where small structures combine to create larger, more complex systems. The role of bars in galactic evolution is not limited to individual galaxies. On a larger scale, bars contribute to the cosmic web, the vast network of filaments, clusters, and voids that make up the large-scale structure of the universe. By channeling material into the central regions of galaxies, bars accelerate the growth of massive structures such as galaxy clusters and superclusters. These processes shape the distribution of matter on cosmic scales, influencing the evolution of the universe as a whole. As we look to the future, the study of galactic bars is poised to enter a new era of discovery. Advances in observational technology, such as adaptive optics and integral field spectroscopy, allow astronomers to study bars in unprecedented detail, revealing their structure and dynamics with greater clarity. At the same time, new computational techniques enable the creation of more sophisticated simulations, capturing the complex interplay of forces that govern the formation and evolution of bars. The combination of observational and theoretical approaches promises to answer some of the most pressing questions about galactic bars. What triggers their formation in the first place? How do they evolve over time, and what determines their eventual fate? How do their properties vary across different types of galaxies and cosmic environments? And what can they tell us about the nature of dark matter, black holes, and the fundamental forces that shape the universe? In the grand tapestry of the cosmos, galactic bars are more than just a fascinating curiosity. They are the keystones of galactic architecture, the engines of cosmic evolution, and the windows into the hidden forces that govern the universe. By unraveling their mysteries, we not only gain a deeper understanding of galaxies but also of ourselves and our place in the vast, interconnected cosmos. As we continue to explore the formation of galactic bars and their profound impact on galaxies, it's essential to recognize how these structures influence star formation on large scales. The dynamics of a bar within a galaxy create an environment where the flow of gas is highly regulated, ultimately dictating where stars are born and how they evolve over time. Bars have a significant role in channeling gas toward the center of galaxies, a process that leads to the formation of active star-forming regions. These regions, often referred to as starburst zones, are teeming with new stars being born from the compressed and heated gas. The central bar acts as a gravitational funnel, pulling material inward, which triggers this intense burst of star formation. This process can be particularly important in the evolution of spiral galaxies, where the bar's influence can determine the rate of stellar birth and the overall activity of the galaxy's nucleus. One of the most interesting consequences of this star formation activity is the way it impacts the galaxy's life cycle. The creation of new stars in the center of a galaxy can give rise to what is known as a nuclear star cluster. These dense, highly compact collections of stars form at the heart of many barred galaxies. Over time, these clusters can evolve into supermassive black holes, providing a crucial connection between stellar dynamics and the formation of the most mysterious objects in the universe. But the influence of galactic bars isn't restricted to just the central star formation regions. Bars have a much broader reach across the galactic disk. As gas flows through the bar, it undergoes changes in density and velocity that can trigger secondary star formation further out in the galactic disk. This allows the bar to act as a sort of galactic conveyor belt, redistributing material and ensuring that new stars continue to form across the galaxy. This redistribution of gas and stars isn't a one-way street. While gas is funneled inward by the bar, the material at the center of the galaxy also plays a role in shaping the evolution of the bar itself. The intense gravitational interactions within the central regions of galaxies can distort the bar over time, causing it to warp or break apart. This dynamism means that bars are not static structures but constantly changing, responding to the forces within the galaxy as well as external interactions, such as gravitational interactions with nearby galaxies. What's also fascinating is that these evolving bars can lead to dramatic changes in the morphology of galaxies. The interplay between the bar, the central bulge, and the surrounding disk can result in the galaxy transitioning between different shapes or classifications. For example, a barred spiral galaxy could evolve into an unbarred spiral, or even a lenticular galaxy over a long timescale, depending on the evolution of the bar and its interactions with other components of the galaxy. In some cases, bars can even facilitate the transformation of a spiral galaxy into an elliptical galaxy. This process is typically seen during galaxy mergers or in galaxies that undergo dramatic gravitational interactions. The bar acts as a conduit for the redistribution of mass, potentially destabilizing the spiral arms and initiating a collapse of the galactic disk. As the system settles, the galaxy may end up with a smoother, elliptical shape, lacking the distinct arms seen in typical spiral galaxies. This dynamic transformation highlights the crucial role that bars play in the long-term evolution of galaxies. Furthermore, the study of bars also sheds light on the larger-scale structure of the universe, particularly in terms of galaxy clusters. These clusters are vast collections of galaxies bound together by gravity, and the interaction between galaxies within these clusters can lead to a variety of galactic transformations. Bars can form or be enhanced during such interactions, and understanding how they evolve in these environments can provide key insights into the behavior of galaxies in dense regions of the cosmos. As we continue to refine our understanding of galactic bars, astronomers are employing advanced simulations and new observational techniques to investigate their properties more deeply. One of the major challenges in studying bars is their three-dimensional structure. Bars do not just lie flat within the plane of the galaxy. They are often tilted or warped in a way that can be difficult to observe directly. However, with the advent of more sophisticated telescopes and imaging techniques, scientists are beginning to see more clearly how bars are arranged in space and how they interact with other structures within galaxies. One exciting development in this field is the study of the connection between galactic bars and the dark matter halos that surround galaxies. Dark matter, which cannot be seen directly, makes up most of the mass in the universe. Its presence is inferred by its gravitational effects on visible matter. In barred galaxies, the distribution of dark matter may have a significant impact on the dynamics of the bar. Some studies suggest that dark matter halos could help stabilize bars, preventing them from disintegrating too quickly. Understanding this relationship is key to unlocking the mysteries of both bars and dark matter itself. In recent years, astronomers have also begun to look at barred galaxies in different parts of the universe. While many of the most well-known barred galaxies are located in the nearby universe, there are indications that bars may form differently in galaxies at different redshifts, or distances from Earth. This suggests that the formation and evolution of bars could be strongly influenced by the environment in which the galaxy resides, as well as the conditions that prevailed at different times in the universe's history. Another fascinating possibility is the connection between galactic bars and the formation of supermassive black holes. As mentioned earlier, the flow of gas toward the galactic center can lead to the birth of a supermassive black hole, which could ultimately influence the overall dynamics of the galaxy. Some studies have proposed that the presence of a bar in a galaxy may help funnel material into the central black hole, feeding it and enabling it to grow over time. This could have profound consequences not only for the host galaxy but also for the surrounding environment, potentially leading to the development of active galactic nuclei, AGN, and other energetic phenomena. The role of bars in the evolution of galaxies also ties into the broader question of galaxy formation. How do galaxies form, and how do the various components, stars, gas, dark matter, interact to create the complex structures we observe today? Bars are integral to this process, influencing the way that galaxies grow, evolve, and eventually die. Their influence extends across the lifespan of a galaxy, from its early stages to its eventual transformation into a more evolved structure. Galactic bars are not just a curious feature of galaxies. They are powerful, dynamic structures that influence virtually every aspect of a galaxy's life cycle. From triggering star formation to shaping the morphology of galaxies and interacting with dark matter, bars are central to the evolution of galaxies. Their formation, dynamics, and ultimate fate are key to understanding the broader processes that drive the evolution of galaxies across the universe. As technology advances and our ability to observe these structures improves, we can expect to uncover even more fascinating details about the role of bars in the cosmic narrative, further enhancing our understanding of the universe and our place within it. As we delve deeper into the formation of galactic bars, we must also examine how these structures interact with the broader galaxy, shaping its overall dynamics and evolution. The behavior of a bar is not a solitary event, rather, it's part of a much larger picture, influenced by various factors, both internal and external to the galaxy. One crucial factor is the role of galaxy interactions, particularly mergers. When galaxies collide or pass near each other, the gravitational forces at play can trigger the formation or enhancement of bars. This is especially true in the case of minor or major mergers, where the gravitational tug-of-war can reshape a galaxy's structure, induce bar formation, or even disrupt an existing bar. The bars that form as a result of these interactions can vary in shape and size, depending on the specifics of the encounter. In some cases, the merger can create a more elongated bar, while in others, it might distort or weaken an existing one. The energy released during these interactions can also enhance the star formation activity within the galaxy, contributing to the overall dynamics of the system. Interestingly, mergers don't just influence the formation of bars, they can also lead to their eventual dissolution. As a galaxy undergoes a major transformation, especially during a merger, the bar that may have been a dominant feature could break apart as the galaxy restructures itself. This process can lead to a smooth, disordered disk, or even result in the formation of an elliptical galaxy. The eventual disappearance or dissolution of bars highlights the delicate balance of forces at work within a galaxy and shows how galactic bars can be transient features, appearing and disappearing as a result of the galaxy's evolving dynamics. In addition to mergers, the properties of a galaxy's environment can also influence whether it hosts a bar. For example, galaxies in denser regions of the universe, such as galaxy clusters, often exhibit different bar dynamics than those in more isolated regions. In a dense cluster, the gravitational interactions between neighboring galaxies are much more pronounced. These interactions can enhance the formation of bars or even alter the orientation and size of existing bars. Moreover, galaxy clusters can create an environment where bars are more stable, maintaining their form over longer periods. Understanding how these environments affect bars provides a valuable insight into the large-scale processes that govern galaxy evolution. Another intriguing aspect of galactic bars is the interplay between their structure and the galaxy's spiral arms. The spiral arms of a galaxy are the regions where stars are more densely packed, often creating a visually striking pattern. Bars can influence the shape and structure of these arms, often creating a resonance effect. This resonance happens when the motion of stars within the bar interacts with the spiral arms, causing them to become more tightly wound or more spread out, depending on the specifics of the interaction. This resonance can also lead to the formation of additional structures, such as ring-like features around the central bulge of the galaxy, often referred to as polar rings or resonant rings. The relationship between bars and spiral arms isn't just limited to structure, it also affects the rate at which stars form. The compression of gas caused by the bar's gravitational influence can lead to an increase in star formation within the spiral arms. This is particularly true in galaxies that exhibit high gas content and are in a starburst phase. The gas flows from the outer regions of the galaxy toward the bar and the central bulge, where it is compressed, leading to the formation of new stars. This dynamic process highlights the importance of galactic bars in regulating star formation activity across the galaxy. Another fascinating aspect of galactic bars is their potential role in regulating the activity of active galactic nuclei, AGN. AGNs are highly energetic regions found at the centers of some galaxies, often associated with a supermassive black hole that is actively accreting matter. The presence of a bar in a galaxy can help channel gas toward the central black hole, providing it with a steady supply of material. This can enhance the activity of the AGN, leading to a brighter and more energetic center for the galaxy. The bar acts as a kind of cosmic conveyor belt, facilitating the flow of material from the outer regions of the galaxy to the very heart of the system. On the flip side, the presence of a strong central black hole can also influence the evolution of the bar. The gravitational forces exerted by the black hole can affect the bar's stability and shape. In some cases, the central black hole can prevent the bar from disintegrating by stabilizing the inner regions of the galaxy. In other situations, the black hole may be the source of enough energy and gravitational pull to disrupt the bar, causing it to lose its coherent structure. Interestingly, the study of galactic bars is not just about understanding the mechanics of individual galaxies. It also offers clues about the larger processes that shape the universe as a whole. The formation of bars is closely tied to the larger-scale structure of the cosmos, including the distribution of dark matter. Dark matter, which makes up the majority of the universe's mass, plays a critical role in the formation and behavior of galaxies, including their bars. Understanding how bars interact with dark matter halos could provide valuable insights into the nature of dark matter itself, a subject that remains one of the most intriguing mysteries in modern astrophysics. In addition to their role in galaxy evolution, bars can also be used as a tool for studying the properties of galaxies. The size, shape, and orientation of a bar can provide valuable information about the mass distribution, star formation rate, and gas dynamics within a galaxy. By studying the bars in different galaxies, astronomers can infer a great deal about the galaxy's history and evolution. For example, the presence of a bar in a galaxy could indicate a certain level of maturity, or indicate a galaxy that has undergone significant interactions with other galaxies. Bars can also serve as markers of galactic age, as their formation and destruction are often tied to specific phases in a galaxy's life cycle. In addition, the study of bars has profound implications for understanding the broader universe. Bars are not limited to the Milky Way or nearby galaxies. They are present throughout the universe, even in galaxies located billions of light years away. By studying distant barred galaxies, astronomers can gain insights into the conditions that existed early in the universe's history. These distant bars may provide clues about the evolution of galaxies in the early universe and the processes that led to the formation of the structures we see today. The study of galactic bars is also leading to the development of more advanced technologies and techniques in astronomy. The complex dynamics of bars require precise observations and sophisticated computational models to understand. As a result, the study of bars is pushing the boundaries of what is possible in observational astronomy, encouraging the development of new telescopes, sensors, and simulation tools. These advancements are not just helping us understand bars, they are helping us explore the universe as a whole. The formation of galactic bars is one of the most fascinating and complex phenomena in astronomy. These structures are not just aesthetic features of galaxies, they are key players in the evolution of galaxies, influencing star formation, galaxy morphology, and the overall dynamics of the universe. Bars are formed through a variety of processes, including the gravitational interactions between stars, gas, and dark matter. Their influence extends far beyond the central regions of galaxies, impacting everything from spiral arms to active galactic nuclei. As our understanding of these structures grows, we are uncovering new layers of complexity that challenge our current models of galaxy evolution. The relationship between bars, star formation, and the broader cosmic environment is a subject of ongoing research, and with each new discovery, we move closer to understanding the profound role that bars play in shaping the universe. Bars are more than just structural features of galaxies. They are the lifeblood of cosmic evolution, shaping the way galaxies grow, evolve, and interact with one another. By studying the dynamics of bars, we gain insight not only into the history of individual galaxies but also into the very forces that have shaped the universe from its earliest moments to the present day. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.